Hey, hello, how are you? Continuing with the operating system development here. The series I'm planning on doing for this video, this episode, virtual memory management and paging. So enabling the use of 4 kilobyte pages of memory instead of physical RAM 4 kilobyte blocks. But before I do that, the reason I have, the full picture here is because I had a request to show booting if the thing actually boots on hardware. So I wanted to show that first off. And it turns out it does boot. So hopefully I can show that. But at the end of this episode, it won't perform as well as here because I have some bugs I got to work out that don't happen in emulation and QEMU, but they do happen on actual hardware on the laptop there. I'll try and show that, how to actually boot on the laptop. Okay, so just move the camera down, and I have the laptop here. Yeah, that's in there. So I just want to double check the date so I can make sure the file's updated when I transfer it over. Okay. So that's there. So I use like Windows for, other various development work and regular work and things. And it's just easier for me to move things onto actual physical drives, like USB drives or hard drives and things, from my Windows host, because this isn't a virtual machine. So for that, I'll just have this here. I have DD for Windows. This is just in my own, folder and everything. That's this exe right here. Typically what I do, just as a sanity check to see what devices I have on, would actually want to move it to, because I don't want to overwrite any of this crap, because this is my actual stuff, and that would mess up my day something fierce, so I'm not going to do that. But if I plug in a USB drive, such as SanDisk Cruiser here, which is probably flipped, but it's a 64 gig USB drive, which I did not have success with. I had success with writing directly to a SATA drive, and I'll show that. But how do I get this, my os.bin file over to my host? I do that from Windows with SCP, which is nice, or I can, go in with SSH. I have that enabled on FreeBSD and everything. But if I SCP in, which I have the command up here somewhere. There we go, SCP in. Oh no, my local IP is leaked. Maybe I'll pixel that out to be funny, but this is just where the stuff is. Oh, that was my test version of the OS. I want the regular one here. So taking that os.bin, putting it in a local file on my machine through SCP. And just checking that the file is updated with the date. Yeah, that's right. That's accurate. That's not. But okay, I plugged in my USB drive. So we should see that show up within the list function here. Somewhere. Typically I look at it up here because it's going to be mounted. This is where it is on F. Over here, this is the USB drive here where it's mounted. So that's device F. So using DD here, whatever's mounted on F is what I want to write to. And it is handy, although I guess it doesn't work all the time, but it is handy to be able to write directly to a device. Input file from this local folder is I have it in bin files. My OS binary is os.bin, the 1.44 meg disk image, if you will. We can do output drive, although it wasn't working well earlier, maybe it'll work now. Output drive F, just F colon. So I'm going to write, that file to the output drive. And 1 megabyte, I guess, is the 1M. So I think it wrote to the drive. I'm hoping. But just in case it didn't, I'll show also the writing to a SATA drive. Just open that back up there. So this, well, actually, I'll probably close it. The ThinkPad X60 here is it was pretty nice. I mean, to access the hard drive on this side, there's a little cover. There's a little cover there with like one screw. I just have that off because taking it off feels like it breaks every time, and I didn't want to be annoyed by that. So basically, you just turn it over, and on the bottom there's a little cover, that little screw hole right there at the bottom. You just unscrew, and it kind of looks like this with the caddy in there. This is just a pull tab, and you can pull it out. It's got rubber grommets on the sides. I think those are called grommets. Wallace and grommets. But you pull that out. I put in an SSD. This is not the original hard drive. This is a 240 gig SanDisk SSD. And the reason I'm using this, although I have a Crucial MX500 that other one, that Crucial, is rated for 5 volts at 1.7 amps. I got a USB to SATA connector adapter here, and it did not work. Or, well, I think it actually did work, but not all the time. It depended on the port that I put this into. It needs enough power through the USB to work. But then I later figured out it wasn't showing as a partition in some things because on Windows I do not have an NTFS partition on the other drive, so it never showed up. But that's, boring. So this one does work because this SanDisk drive specifically is rated for 5 volts at 0.7 amps. 0.7 instead of 1.7. And it worked on more USB ports because they needed lower power or something. As far as I understand it, I could be wrong, and I could just be dumb, but these are powered, so you have the power and the data, or vice versa, however that works. You line them up. This is nice. It's got these little like teeth thing on the end, which point into the bottom and top of this. You can line it up and just snap it in. So that works. I plugged it into the front USB port on my computer. And if I go back and do the list command again, it is going to be this bottom one here. Device hard disk 4, partition 0, block size 512, 240 gig. So this many bytes approximately. So I'm just going to write the same file. Also to this, which I have as a command here. And all you can do for that is just, you can copy paste this text and it's fine. Control C, Control V. But it will write 2880. So that's a little different too. Writing to the USB had 1M for, I guess, a megabyte. And this has, the actual block, the block size, 512 times 2880 is 1.44 megs approximately, is why I chose that size. So it could be an issue with block sizes and things that I'm not doing right with the USB drive, but there you go. So unplug it, put the cable back, put the sidewall rubber thing on, which is cool. It reduces vibration, keeps it snug in the laptop case. But I'll plug that back in. Awkward to try and hold this, but slide it back in effectively. This has, which might be hard to see or not be able to see at all. This is probably a terrible way of doing this, but if somehow you can see in the back there, probably not. It's probably not going to focus right. But there is a SATA connector in the back, so this slides in and just like goes snug against that and works. I keep bumping my mic. Professional as always. This is going to be like 30 minutes of me fumbling about. Okay. But you just slide that sucker back in there, and pull tab, and just push it in, make sure it's all the way in, and yeah. I think this is now flipped the wrong side way again. Should have been doing this the whole time, right? But that's in there now. With the little unlock switch there. I don't make laptops like this anymore. But I'm also 60 years old on the inside, so that boomer status, right? So I'll plug in, I'll try it from the USB, I just don't think it's going to work. I don't know which, there's like 3 ports on this, I don't know which would be the best to try. I'll try it on one of these left ones, these right ones here, over here. Here you go, so that's right there, that's right there. Okay. See how the screen looks as well. On this one, you press F12 to go to the boot menu. So this is awkward because the video cable for this is not the longest and it does not have very much slack. So I tried to move this back, but it's gonna rip it out of my computer. Yeah, trying to film lighting is not great. But the SanDisk there is the USB and the ATA is the internal SSD. So I'll try it from the USB first. We'll see if it works or not. Okay, it does boot. Okay, that's good. The resolution for this laptop as a max was 1024 by 768. That's what I'm going to put in there. 32 bits per pixel, is fine. It works with lower bits per pixel values as well. But there's nothing really showing on the screen, which is great. It's just blank. Until you wait a few seconds and you get the date time. I don't know why it does that. It boots up in a different way than on the emulators, of course, and the emulators don't show that unless I tell it to show that. So I can type in text, but you won't see it on the screen, which is very nice. So I have to type in commands to like change the colors to get everything to work right. No, so stuff does not seem to be working here. So, and I had issues booting from the USB as well, so I'm just going to try again from the SATA. I'll unplug the USB. It could be the port I'm doing it, and it could be not properly handling ATA operations and the USB doesn't properly simulate or something. I don't really know. But by default, this should boot from the SSD, which it did. So still nothing, but I'll wait a bit for the time to come up. And there we go. So this time, if I do show date time, I swear it was working earlier. Or at least I thought it was. I can try some lower resolution. 800 by 600, 16 bits per pixel. So we can see those glorious graphical errors that I have as well. Yeah, it's not doing anything. So that's good. And this did work earlier before recording, which is, you know, you got to take my word for that, right? So I'm going to try writing it to the drive again and see if we get any different results. Okay, I rewrote it to the disk and rebooted a couple times. I'm not going to tell you what I did differently because I don't think I did anything differently, but it takes in commands now. Maybe I have to type in something before the time comes up and then it's okay. I don't know. Obviously it's buggy. Hopefully it works a little bit better at the end of this video, but I just want to show that, hey, you can't see the text, but if I type stuff in, it is scrolling, albeit slowly, but it does work. If I try to change the colors, I'll put in 6 3s for the foreground color, you know, kind of darkish gray, black. Put in 6 Ds for the background color, sort of a creamish, you know, a little grayer than white, not really cream, but you don't see anything, right? But you do see that it redraws the time in the new colors, so I know that's working. I'll just clear the screen and print. Just so hopefully you can read it better, right? A little bit better. I know the lighting's like crap because it's just capturing this on camera is like really bad. But anyway, that's a directory there. It does write, it does boot, right? This is still, you know, full physical manual memory management. I'm going to get rid of the date time here. We can print files, I think. Does anything work though? The calculator should work. I usually do some sanity checks. 20 plus 100 divided by 2. This might be 70. Yeah, 20 plus 50. Okay. Control R to go back. All right. Let's write some file here. Create a new file. Controls down here. Control S. Test file 1. TXT. We'll go back. That's at the bottom. So if I run it, okay, that does print. The file table does not print for some reason, although I think that was a bug that I did fix that I will show in this video anyway. I'm messing up the focus. Sorry about that. It does print files that we can write, but anyway, just for that one person, if I'm not rambling and being too confusing, I use DD personally to get the file and write it to either USB or SATA hard drive directly, which seems to work better in my opinion. It's more stable, for me at least. And then I just boot it. I mean, this PC, this laptop here supports legacy booting. My newer laptop does not. It only supports UEFI, so this does not work on that one because it doesn't go through the MBR, reading the 55AA and loading 512 bytes and everything. It boots up into UEFI, and you have to do that, which will be later on. I'll make a slightly different set of videos or series for 64-bit UEFI. That might not be till next year. I'm not sure, but this does boot. So I just wanted to show that. I didn't think it would because I know the boot sector stuff does, but this uses actual ATA programmed I/O for the ports to read and write sectors, and that does work, at least right now. Okay, so one last thing here before I get to the software part of this video. Mic quality is not as good on the camera, but the sound does actually work on this for the PC speaker. It's also, there's no volume control for the PC speaker, so I don't know if this is emulated or what, but it's loud as shit, so but I'll just show it does work. If I turn it on, the volume controls, it's very loud unless I turn it off. It does get louder though. So that's the quietest it actually gets. But at risk of giving DMCA, I'm gonna turn that off. It does go, and it goes for the right timing and everything, so I at least got the millisecond timing right. I know I didn't show the sleep tests right, and this is gonna, you know, it's blocking IO while it plays that, but the timing is good for the PIC, the PIT as well. The timing is fine, so just wanted to show that the sound also works, albeit it's loud as crap because it's the PC speaker. All right, so I guess maybe I kind of lied at the end of that last part because I worked on things a little bit, and I did get things running smoothly on hardware for this, you know, paging and virtual memory and everything. It is working now. I had a couple bugs to work through, and I got them figured out, mainly to deal with some global variables and included files that weren't being set right for whatever reason. But I got that worked out, so it's good now on hardware. Hopefully I'll show that, you know, live and recording live at the end of this video, but we can get to paging, right? So virtual memory segmentation for x86 paging. Why is it useful? Why do we need it? Why do I want to do this for my operating system, even though it complicates things? Well, it allows you to basically use whatever address you want in sort of a loaded program or process that you're doing. You can use any address in the full address space. For me, I have a 32-bit operating system, which lends a 4 GB total address space. So with physical memory management, you can allocate, you know, 4 KB or however big chunks of memory, and you do the same with paging, 4 KB pages instead. But paging is more for virtual memory, so you can have multiple things using the same addresses, multiple processes, and that'll be fine, because the virtual addresses for each process will be mapped to different physical addresses in memory. And I'll get more into that as we go along, but paging structure, this is, I'm just have, you know, the osdev wiki pages on paging. This is kind of hard to read here at the bottom. Zooming in a little bit. So your CR3 for x86, this is a machine register, CR3, control register 3. You send it the address of a page directory, which has 1024. For me, you went 32, so 32-bit. 1024 32-bit entries. And each one of those represents a page table, which a page table contains 1024 ints. And each one of those points to a 4 KB page. So this 4 KB page will represent the actual physical RAM address, a 4 KB chunk of physical memory. But you can map that 4 KB chunk of memory to any virtual address effectively within your address space. And the memory management unit, MMU, sort of makes that work. It looks at whatever address you're using at runtime, and it goes through the page directory into a page table and looks at the actual, what's called a frame, the physical frame for that address, and says, okay, you're trying to access 3 gig in virtual memory. What does this 3 GB address represent? Maybe it goes through and says, okay, this actually represents physical address 20,000 in hex or something, and you have read-write access, and it's in user mode, so you can go ahead and access this address. It's fine. But one thing paging also gives you is different flags you can set here. It's easy enough to read. Present, we have read-write, user, or supervisor. So if it's available from ring 3 or ring 0, I'm going to be doing still everything in ring 0 because it's easy and I don't have to worry about it right now. I'm not going to be using 4 MB page directories for like huge pages. I'm just going to use regular 4 KB pages, although you can mix and match if you set a flag somewhere. I think in CR3 or CR4. It's either physical address extension or page size extension, PAE or PSC, I don't remember. There's 64-bit paging. You need to enable physical address extension in long mode. You don't need to enable it in 32-bit mode, but so I'm not going to. Paging allows you to use whatever address you want pretty much within a running program or process. You're not beholden to whatever's available in physical memory. You can use address 0, you can use address 4 gig, you can use address 10,132.5, it doesn't matter. Because the processor will look at whatever address you're using, treat it as a virtual address, and say, okay, what is the actual physical address here that this is attached to? What access rights do you have to that address? So it's kind of a way of separating access rights, read-write ability, user kernel, user supervisor, different sort of things like that. The different flags here, present will be, is it actually present and being used for a page? Specifically, a page meaning a 4K chunk of memory here. Read write, user supervisor, write through, which I think is used for like copy on write or something. Write through caching. I don't know. I don't know anything much about caching, so I'm not going to go over that because I don't know about it. Read write permissions, basically, and user supervisor, kind of the only two flags I'm going to be using in this video. Page size bits, you can use 4 megabyte pages. Is that up here? PS right here, PS0. So if we set that bit, it will count as sort of a 4 megabyte page entry. And the address bits will be in different places. But these are all, see, 0 to 31. These are all 32-bit, just ints, just numbers that represent, a page of memory. Eventually, I do want to load my kernel to 1 megabyte or 100,000 hex, but I am going to be remapping the kernel address to virtual memory address 3 gig, like they're doing here. This is 3 gig. Higher half kernel is what I'm going to be doing. So for like a multitasking operating system, you probably want to map your kernel into every single process's address space. So, and I'm not going to be doing that in this video, but in the future, if I want to do multitasking, which I kind of do, I'll probably set up either a page table or a full page directory for a process, and then within that page directory, I will map a page table, or however many page tables for a process, and I will map in the kernel to 3 gig, or at least the same address within that process. So the kernel will be at the same spot in every page directory, such that you can call in and do syscalls correctly and just be able to do kernel mode things within a process. But in assembly, you're basically setting, you have an array of all these page tables. You need to get to the right one and then map wherever the kernel's address is. In this case, it starts at 1 meg, and you map it to the 3 gig address. And since we're working with 4 kilobytes at a time, 3 gig is going to be around the 768th table within your page directory. So it's just setting addresses. You basically just set, the virtual address and the physical address. So yeah, everything up to bit 12 is flags. After that, we have the address. So I didn't explain that the best, but I mean, trying to give you the motivations for paging. Why would we want to use it? So you can use whatever address, and you can use multiple processes using the same addresses. They can be looking at different memory parts, and it's just, it enables isolation of concerns, separation of concerns for like read-only, read-write, user supervisor mode, which is kernel. Enabling paging isn't bad. You just move the page directory, which again has entries for page tables, and the page tables have entries for physical 4 kilobyte chunks or pages of virtual memory, which point to physical memory when you fill them out. But the top level here, the page directory, you're basically moving the address of your array, we'll say, into CR3 register. And then CR0, control register 0, you're going to enable paging by setting the top bit. The protection is bit 1, I believe. But that should already be set when you go to protected mode, like I did. So I'll really just have to OR it with 8. If the protection flag is clear, you'll get a general protection exception. I will also have to set a page fault handler, because it'll generate an exception 14 if there's any issues with accessing a page of memory. Page size extension for 4 meg pages, you can do this. I'm not going to be doing that in this video. 64 bits, slightly more involved, but not really. Pretty easy, but okay. I'm not going to be doing physical address extension. In the future, if I go 64-bit, I would, but virtual address spaces, again, motivation. You can have 2 processes pointing to the same physical memory. Well, sorry. using the same addresses, but have different views of the memory, if that makes sense. See, these are kind of interwoven together. This is the actual memory, but they're only looking at different addresses here, even or odd addresses. That's cool. You can use the same addresses and have sort of shared read-only libraries like DLLs and things. Those, I think, use paging. You can swap RAM to disk and back from disk. So if you try to access a page that is not present and you get, a page fault exception thrown from that, you can, in your page fault handler, you can say, okay, I have this address for the page. If the process that is using this page has the right access rights, I can say, okay, this page is valid. I should grab it from disk and load it to this address and then return to the calling process, and it'll be able to use that page as if, you didn't have an error. But you can use a page fault handler to kind of swap in pages. That's kind of what swap space is. You're swapping in these 4K chunks of memory to and from disk to sort of extend your RAM using your hard drive, your SSD, your more permanent storage medium. That's another reason to use paging. It makes swapping to and from disk easier. And you can, extend your RAM that way. And page fault is exception 14. So if something does not have the right access or a page isn't present or other situations, it'll generate a page fault when you access a particular address, because all addresses, when paging is enabled, all addresses right after this code here will be counted as virtual addresses. So you need your paging set up before you do this, or else you'll get a protection fault or a page fault, and you'll have a bad day. You'll probably just have a triple fault and reset because it won't be handled. So, and I will make a small basic page fault exception handler. I'm really just going to print to the screen what the address is and what the error code is. So I'll go in and map in the pages later when I'm sure it's working, right? I just want to make sure it works first, and we aren't generating page faults by the end of this video. But if you do get one, the error code on the stack will be two bytes, and you can look at the lowest 3 bits here, so 0 to 7. You can say if it's all 0, then we have a supervisory or ring 0, a kernel process tried to read something that was not present. If it's set, then you tried to read something that was present and it just caused a fault. Bit 1 is read write, so if bit 1 is set, it would be writing. If it's not set, it would be reading. And then if bit 2 is set, then it would be a user process. So the only page fault exception, the only error codes I should see from paging this video should be 0 or 2 if we're trying to read or write something that isn't present, because I don't have anything in user mode, so the third bit will not be set. But okay, when you're mapping pages and you're unmapping and you're swapping to disk, if something is not true anymore, like if you unmap a page, if you're done with the memory and you want to free that memory, an address that was mapped, a virtual address that was mapped to a physical address, it's called mapping. I guess I didn't explain that. When you associate a virtual address with a physical address, it's called sort of mapping a page, mapping that address. When you're done with that memory and you free it up, you free up the physical space, or you just want to save it for later or set it as non-present or something, you unmap it. And by unmapping it, we're going to also invalidate it. Unmapping, I'm just going to free up the memory that was allocated towards it physically, but sort of to go along with unmapping, I'm going to invalidate the page in the translation look-aside buffer, which is the TLB, which is a space in the x86 processor, that holds sort of valid addresses. It's cached. So the memory management unit looks through the translation look-aside buffer, the TLB, to see if we have a page in the cache that you're trying to access, and if so, it's faster to access it because it's been cached. But you want to make sure that anything that's in that cache is actually correct. So when you unmap a page, you're probably going to want to flush that page or remove it from the TLB. This is, there's an instruction for that, and we'll just use inside assembly, similar to what they have here, invalidate page instruction. So that's for a single address or a single 4 kilobyte page at a time. If you unmap all the pages in a page table, you can probably invalidate the whole table or everything in a directory, like for a process. When that process is done, if you allocated a directory for it, you can unmap all the pages within that page directory. Or another way of invalidating everything in the TLB is just to move a new address or a new page directory to the CR3 register, and that should, right here, That should invalidate the whole page directory, maybe slower, although they didn't time it, so I don't know. But that's an easier way to do it. Copy on write and other things I'm not going to get into because I haven't gotten that far yet. But yeah, that's my 15-minute spiel over motivations in one osdev wiki page over paging. They also have pages on setting up paging. I'm going to do things similar to how they have it, but also I use the brokenthorn guide just because I thought it was good. And all these will be links in the description, but I did my things similar to what they had because they had a full setup and it seemed to work. But it'll be kind of quasi like how they did it and quasi like how osdev wiki did it, make an unholy union between those two. I will be doing identity paging as well for the first 4 megabytes of memory. So we have 1,024 entries in a page table. Each entry handles 1 page of 4 kilobytes. 1,024 times 4,096 is 4 megabytes. So the first page table, or the first 0 to 4K of physical RAM, I'm going to set the virtual address to the physical address, which is what identity paging is. If you set the virtual address B8000 mapped to the physical address B8000, it's the same address. So that's called identity mapping, identity paging. I'm going to do that for the first 4 megabytes of memory, just make things kind of easier. I don't have to worry about stuff that the kernel's going to use in the beginning of RAM, like the interrupt table and other things, if I want to put them there. If I want to put whatever into the first 4 megs, I can do it safely because I will identity page the first 4 megs. I will also be identity paging the VBE frame buffer, just so that's associated with itself and I don't have to worry about that. But I think those are the only things I'm going to do with identity paging. But that'll come up in a bit. But basically, yeah, page directory is an array of 1,024 uint32s, effectively. They aligned it on a page boundary, which is smart. I don't know if I'll be doing that. They're enabling every table within that directory effectively by setting all the elements of that array. So all the page tables that this is pointing to, all those uint32s, they're setting the present bit, which is bit 1. No, they're only setting bit 2, which is write enabled. Present bit would make this 3 because that would be bit 0. So they're setting it read write is all they're doing. And by leaving bit 3 off, only the kernel can access it. Okay. And I'm getting that from page table entries stuff. Bit 0 is not set, bit 1 is set, making the value 2, and bit 3 is not set. That's where I'm getting those flags from this. And they're making a page table. They're setting that to physical address ORed with 3, which sets it as present and readable writable, and not user, so supervisor level, leaving off bit 3. Not sure, enabling. So this is a good page. I'll have it in the description as well, just for another thing to look at to make things understand. What they call page frame allocation is the physical memory manager that I did, and I should have looked at this page before I did that, because it just, just another resource there. But page frames, the frame inside of a page is the address that page is pointing to. So that's what a page frame is. And identity mapping, identity paging will be setting the frame equal to the actual physical address that the virtual address points to. Otherwise, the virtual address can be whatever and point, as long as it points to a valid physical address. But anyway, I'm rambling on too much. I'll get started here. As opposed to my usual method of using notes on the other screen that you can't see, I'm going to be having a diff basically for everything. I went and made a testing branch through Git, and I just made commits to that. And whenever I made bigger commits that fit together, I squashed them down. So this page basically has everything that I've changed since last time. And I'm just going to go through and explain things and type them up and maybe switch some things around to make more sense and all. But so yeah, instead of looking at notes, I'm going to be the human patch, the human diff maker for this. If you want to know what I'm doing, I'll be looking at these and like crossing stuff off my list whenever I got a file done. So I figured that was easier. I can have everything on one page to look at instead of moving between different screenshots and windows and stuff. So If you want to get latest updates for this, I'll try to remember to update what I put as the testing branch. So you can check out that branch specifically through Git, and I'll be updating that more often than the main branch because this will be for testing and in between videos. You know, caveat, I'll probably be rebasing and doing things to this branch a lot. So don't rely on it, 100%, but just every so often you can check it if you want to see more updates between every couple months that I do these videos. So now that I've talked for probably over half an hour and lost 99.9% of the viewers, now I'll actually get to typing up stuff. My game plan for this is going to be making the virtual memory manager first. So I'm going to put it within the memory folder here. It'll be virtual memory manager.h. I'm going to make the virtual memory manager, which will handle mapping and unmapping pages and enabling paging, just functions for those things, as well as set up the page directory and page tables and stuff, definitions for those. After that, I will add a page fault handler, which will be exception 14, so it'll go in the exceptions file. And then when those are done, I will add the exception handler, enable it within the kernel, and use the virtual memory manager we make. I'll use that in the kernel and enable paging, and switch loading programs from physical memory blocks to pages, which, behind the scenes will be physical memory allocated. And then after that, I want to make a malloc and free implementation. So I'm gonna use a basic simple linked list for malloc. I'll probably put that within the memory folder. It'll be like malloc.h. So I'll make a couple syscalls for that, for a program to call in and dynamically allocate pages of memory to use. Or well, just bytes, really. I'll have the same malloc interface, just call malloc with 100 and return a pointer to 100 bytes, right? And as well as free. So I'll make syscalls and C functions for malloc and free. And I will change the editor to use malloc and free for files that are edited. So instead of hardcoding 20,000 in hex or whatever we have in the editor, I'm going to be calling malloc for however big the file is that we're loading or editing instead, and we'll use malloc for that. And then after programs return within the kernel, I'll check if there's any memory that was allocated. We'll free up that memory so we don't have memory leaks. I might make a little small program to just print crap to the screen for multiple malloc and free calls, just to test that like 3 or 4 malloc and frees in a row, what have you, doesn't break anything or cause any page faults. And that should be all that I do this video, because that'll probably end up being 3 or 4 hours anyway that I have to edit down, but that'll be all right. And then, sprinkled here and there will be bug fixes and tangents and everything like there usually are. But yeah, I'll make the virtual memory manager thing. I guess I'll do that. We'll do a virtual memory manager. Actually get to typing. We'll edit that file here. Virtual memory manager.h. These will be definitions and functions for paging, virtual memory, mapping, unmapping pages, etc. Okay. Remember the pragma once, praise the pragma once, it's all good. We'll probably be using some uint32s here, it looks like. So I'll include that. C standard bool. So I wanted to have include files like this as well. So I guess this will be my first tangent, right? Before I even start doing this. Because right now I have to do this, which is kind of annoying for every single include file. So I did find a way to get around that and fix that. But I'll put in the other files here first. I am going to be doing the physical memory manager as well, because I'll have to allocate physical blocks of memory for each page if it's not already allocated, and then map, the addresses together. So I will be allocating blocks. So I will be calling on functions from here to do that. And yeah, but I guess before I do that, I think we're in the top level, yeah, build. Let me fix that here. So in the makefile, I don't like including the .include into the folders. It looks a little bit better if we can just take folder/file, right? For a file system for include files, it just looks a lot better. So these flags, I'm going to add in capital I, and then include. Yeah, I believe that should work. And that just says I'm going to include, start looking when you're going through include files, start looking in this folder. So in all the files that I'm including files within, they're in like the source folder, right? So it'll go one step up to our top level and then go into include and then look for the files that we're including. That's what this is saying here. If I go into here, I shouldn't need to include this stuff, right? But I'm just going to, even though there's nothing in here, so it's not going to matter right now, I'm going to include this within the kernel. Just to show that stuff should work. Exit out of here, go into the build folder first. So stuff should work here and compile normally. Right, but also if I get rid of, you know, the .include, which is now being searched for these include files, now I should be able to type stuff just like this, and that looks a lot cleaner and better. It's kind of, you know, bike shedding, mate. Well, it's kind of yak shaving, but it compiles and it looks a lot cleaner, so yeah. But anyway, yeah, let's get back to that. So okay, there's 1024 is the max, the number of entries in a page table and a page directory. So pages per table, we'll say, is going to be 1024. And the number of tables in a directory, I'm kind of going along with the brokenthorn stuff here, but tables per directory also is going to be 1024. I'll just each page size is going to be the same size as our physical blocks that we've been doing before, same as the block size in the physical memory manager, which is 4096, but I'm going to call it page size instead for make a little more sense here in context. But 4K, 4096 bytes per page. I'm not going in the order that I wrote the file before, so I'm confusing myself, which is great. I could do defines, or I could do like enums or something. I'm going to do enums here for the flags that are part of the page table and page directories. There we go. Okay. So these flags here, the lowest 0 to 11, the lowest 12 bits of the page directory and the page table are these flags. So I'm going to make a couple structures for those flags. Well, a couple enums just for the values of these. So the present bit is bit 0. So present will be 0. Read write will be 2. User supervisor will be 4 in hex or decimal because it'll be bit 3, so on and so forth. So I'm just making kind of masks for these flags. Two enum sets here for the flags so that I can just have integers, just values that I can or and with to set or clear these flags. That's all I'm doing right now. So I'll have enums for those. And then if I want, I can restrict values for parameters and stuff to just these enums. So that's also why I'm not doing defines here. I can be like, oh, you're specifying a flag that doesn't exist. Don't do that. I'll have a thing for page table and page directory, which I'll probably use just dir. But page table, or pt, I'll use as a, you know, little thing for that. Page directory, I'll probably do pd. So page table entry is what pte is. Page directory entry is what pde is. And then entry being one of the 1024 entries in, say, a page directory array. Just do like that, right? So one of these numbers within the array will be an entry. So that's what these, you know, 3 letters stand for. Page table entry, page directory entry. But the present bit is going to be if the first bit is set, so 1, effectively. The read write will be bit 2. Yeah, if it's 1 base to be bit 2, this will be 2. The user supervisor flag, I'll do user. This value will be 4. Write through that I'm not really messing with will be the next bit, so that'll be doubled, that'll be 8. And I think it's cache disable, which I'm also not messing with, but that's the next one, which is 16. And we have the accessed bit. Was this bit actually accessed? The CPU will set this, I think. I don't think we have to set it. No, we don't. That's 32. That's the next bit. The next bit is the dirty flag. Has data been written to this? I think that's what it says. If the data within this address has been affected or this page has been accessed, maybe I think the dirty flag is set. It might go with the read write flag, so that if it's writable and you wrote something, then the dirty flag gets set. I don't remember, but I think the processor sets this. We don't have to mess with it, but I'll put it there anyway. Then we have page allocation table, or whatever this was, PAT, page attribute table. So you use the page attribute table along with cache disable and write through to indicate the caching type, which I'm not going to mess with, so it'll probably just be set to 0. Because I don't know enough about it to want to mess with it yet. But page attribute table bit. The global bit that I'm not going to mess with either. And double that again. So this is what? 256? Alright, put output into decimal 100. I think you pipe that to BC, or do you just do equal? That's a bad expression. We don't want that. Okay. What if I do this? I don't remember how to use these calculators, and I want to get better at them. Although DC is reverse Polish notation, right? So if I do 100p and then quit, it gives 100. And if I set the output base to 10, 10.0, it says 100, so that doesn't work. If I set the input base to 16, 256, okay. Hexadecimal input 0x100 printed as decimal, base 10 output is 256. So yeah, that's what that is. Trying to stick all within Unix here so I get better at it. But then after the first 12 bits here, anything after just means like the actual address or the frame that our page is going to be pointing to. So I'm going to call that the frame. And every bit that isn't bit 0 through 11, so bits 12 and up, and this 32-bit number that I'm working with will be 7 with 4 Fs and then 000. So each hex digit is 4 bits, so bits 4, 8 through 12, or 0 through 11 are the lowest 12 bits for these flags. Every bit that isn't 0 through 11 represents this address here in the page tables that I'm doing. These look a little bit different if you use 4 megabyte pages, but that's all right. I'll just put bits 12 and up. Okay, and then we'll have similar things for the page directory flags. Pretty similar. Similar enough that I can probably copy all these and save a little bit of time. The only differences will be the dirty bit. Only used for 4 megabyte entries. Interesting. 30 bit. So after that, we have a page size bit, which says if we're in 4 megabyte or 4 kilobyte or other pages. If the size bit is 0, we have a 4 kilobyte page. If it's 1, we have a 4 megabyte page. Global's still at 256. That is a 4 megabyte entry only bit. And after global, we have a new one. We have the PAT up here. And that is at 2000, which is also only for a 4 meg entry. I think I have to put commas after all these, but the compiler will tell me if I'm wrong. And then we have a frame, and the frame is also at bits 12 and up for these. Although the frame's a little bit different in 4 megabyte pages, there's a reserve flag right in the middle. So, I need to add that, but I'm not. We'll just set that. So yeah, it's going to be, we need a constant expression or enumerator definite. Yeah, end of enumerator def. So we need, I'll just put it at the end of all these, some commas. Okay, that works. Oh, it doesn't like it because I need equal. These aren't defiance. Yeah, I don't remember how to program in C, guys, I don't know what I'm doing. Especially when I'm talking at the same time, because it definitely just never works when I try to do that. That's why I have the compiler to tell me that, I knew this was bad. All right, can I make enums successfully? I can. Does it boot with an enum? Oh, it doesn't boot because I messed up making it too many times, and the file table's huge and it can't read anything. So I have to remake a file table, and that is why it doesn't work, and now we're good, okay. my unit test is just booting and seeing if it boots. That's my unit test, which is not great. All right, so now I can go back up and make stuff that I was going to fill in here. Just to make it make more contextual sense here. They are, for my purposes, going to be 32-bit for my 32-bit OS, the page table and the page directory entries. I'm going to make a PT entry and a PD entry, which are both going to be uint32s, just to make things make more sense. Page table entry, page directory entry. And I don't really need this. The brokenthorn tutorial kind of did this. I don't really need this, but I'll include it anyway in case I use these. Because sometimes it's a little confusing whether something is searching for the physical address given a virtual address or vice versa. So I'll just include these that I can say, okay, this uint32 for this function is technically being used as a virtual address. So it might make more sense contextually. So I'll just do this, virtual or physical address here, and yeah, they're going to be 32-bit for my 32-bit. So functions, I'm going to make some macros here to set or clear some things for these flags. So the index, so the page table that is at a specific index within our page directory, because there's 1024 entries for each page table in the directory. To get the right index in the directory, given an address, given a virtual address in this case, so maybe I'll call it vert address. Since the frame for a page table and directory here is just everything above the first 12 bits, we can just take that frame, or this address, and shift it right by 12. So that'll get rid of these lower 3 zeros, and we'll just be left with whatever the address is, if we AND it with this value. We don't really need to AND it, but we can just shift whatever we have over by 12, and that'll effectively be the address here. So we'll have the virtual address shifted over. For the page directory, it'll actually be 22 bits. I don't remember why I did that. Let's say I have something like 3 gig, which is, this thing up here. What if we right shift that by 22? I get 768. Okay, that's what we're doing. So I am getting the entry within the page directory that a page table will correspond to from 0 to 1024. By shifting right by 22, we effectively take it mod 1024, effectively. We divide by 1024, I think, is what this is doing. Although 2 to the 22 is greater than that. Right? 2x to the y is 4. Okay, maybe we're okay. We're like modding by the 4 gig space. I don't know what I'm talking about, and I don't know math, but effectively, if we have a situation like where we have the kernel at 3 gig, we need the space. We need the right entry within the page directory that we're getting. And to get that right entry, I'm shifting right by 22. The math works out. I just can't explain it because I'm a doo-doo brain when I try to talk. That's kind of what gets you this 768 from your initial 3 gig value. That's why I'm shifting right by 22. I'm taking a virtual address and getting which entry in our 1024 0 to 1023 entries in our page directory. I just can't tell you how the math works because I'm a doo-doo brain. Let's round that by there. So to get the page table frame, page table index, effectively, what I'm taking is shifting by 12 just to get rid of the lowest 3. Yeah, shifting right to get rid of the lowest 12 bits for the flags. We don't care about the flags, we only want the address here. That's why this is getting the frame, effectively, from a page. Well, it's also how we can get a frame from the page, but that's getting an index within a page table. But we want to limit it to 1024, so to do that, I'm going to AND it with 3FF, and 3FF is 1023. Which means I need another parenthesis here. So the max index is, there's 1024 entries, so the maximum index within a page table or page directory is going to be 1023. So to limit it to 0, 2023, we AND it with 3FF. Not good at explaining, that's all right. These might not be virtual addresses now I'm thinking about it. We could use physical. I just called them address, which made it confusing, but these might be physical. I'll just have address. We'll see later. To get the physical address from a page, effectively the frame from a page, I could call this get frame or something as well. I'm going to be giving this a directory entry, and in the places I'm going to be using this, I'm going to be using pointers, so I'm kind of dereferencing the entry here, dereferencing a pointer to a 32-bit value, so that's why I got the star here. It doesn't make sense when I don't have it typed out, but I had these first, so. I can AND it with not FFF, which will have ones in every place except the lowest 12 bits, which will be 0 because I'm inverting these bits here. So this directory entry will end up being a 32-bit value. I'm basically taking everything except the lowest 12 bits, which will be 0, and I'm ANDing it with that to basically get the frame from a directory entry. And that'll be the address that's associated with it. So that's what this is getting. This could also be called frame, I guess. Clear lowest 12 bits, only return frame address. Okay. And then I'll have a couple functions to set or clear these flags within a page table or page directory entry. I'm going to call it set attribute. So each entry is 32 bits, so just a generic page table or page directory entry here, and whatever attribute we want to set. So one of these masks, one of these flags that we want to set or clear. To set an attribute, I will OR it with this mask. So if I use pointers, which I will later on, given an address to the entry, we will dereference, and we will OR it with the attribute to set that mask. And then consequently, to clear an attribute, we will AND it with the logical not, well, not logical, bitwise not of that address. So that will clear, that'll have a 0 in the bit place instead of a 1, and it'll clear that flag, that mask, instead of setting it. If I want to test it, maybe I'll have something that I want to test. An attribute, if I want to see if it's present or read-write or something. We can just return the entry ANDed with that. We don't set the entry, we'll just return the result if it's set or not, 1 or 0. So basically a Boolean result. AND it with the mask, the attribute. Okay, and if I want to set a address, if I had something called like set physical address, I'm going to call it set frame. So I should have called this like get frame, but I didn't in my notes. In my diff, I didn't call it that, so I'm not going to. If I want to set an address within an entry, I'm going to use set frame here. Again, I'll use pointers. I'm going to set an entry equal to itself, ANDed with not, this value. If I do not this value, it's going to put zeros in all these places that the ones were in, and it's going to put ones in these places that the zeros were in. So what this does is set the lowest 12 bits so that I do not affect whatever flags were set within this entry. The flags will be kept the same because they're all going to be ones, and I'm ANDing with those ones. But in addition to that, I'm going to OR with whatever address we're setting. So that'll have zeros in this place, and I will OR it with the address, which will fill in ones with this place that match the address, and the flags won't be affected. So that's only setting basically the top bits 12 plus. So yeah, only set address frame, not flags, if that makes sense. Yeah, okay. All right, so the actual page directory and page tables themselves. Each page table will handle 4 megabytes of memory each, 1024 entries times 4096. So I'm going to have some type defs for these. You could do these a couple different ways. OSDev Wiki just has straight arrays. The brokenthorn series that I followed kind of had structs that contained arrays. And I think that makes a little more sense when you use them within functions and things. and it makes it a little easier to just get pointers to the overall array structure of a directory or a table. If you just make these arrays, like 1024, I mean, we could type-def this to get like a pointer to a page table, but the type-def pointer would be a pointer to 1024, and we couldn't use it like just a pointer to a page table. It would be more awkward to dereference and get a specific entry. So to go around that, we can stick that array inside of a struct, which makes a little bit less sense. And like osdev wiki had, I should probably page align these things to like a 4K address, and I'm not. But what we can do here, since we have type-def page table entry as uint32, we'll have an array of these entries. So uint32 will make an array called page table. Sorry, we'll make an array of entries. This will be a page table, not a page directory. I'll do that in a second. And we'll have 1024 of these, or pages per table are defined, we set up 1024. And yeah, that'll be that. So when we access an entry within a page table, it'll be easier to set up directory. It'll be easier to set up pointers for these things, like page table pointer table. We can do this because we set it up like this struct, and when we dereference it, we'll dereference like an address to the table entry, whatever entry we get. So maybe it's like PT index for some address, like a what would a 2 gig address be? Like 8? What would 0x? I think that's like 2 gigabytes. But if we want to get the page table there, you know, we'd send that in, we get the index in the table, and we'd get that entry. We get an address to that entry. It is a mouthful here, but if we just did this as a regular array, you'd have to first cast it, I think, to like uint32 table and do like other garbage. So the reason I'm doing this is, one, because the tutorial I followed did this, and also because it made it a little bit easier to understand later on when we use these things within functions and stuff. So that syntax may not be right, but hopefully you get the idea. We'll have similar things here. One similar thing for the page directory, which will handle 4 gigabytes each, 1024 page tables, which each hold 4 megs. And that ends up being one page directory for our 32-bit address space, which makes this a little simpler for 32-bit OS, which is nice. We really just need to be using one page directory at a time, which is fine, and we set CR3 with whatever page directory we want to use. This will be PD entry page directory. This will be tables per directory. But we'll have an overall, like a current page directory that we put into the CR3 register, which says, okay, we're looking at this page table setup for these virtual addresses mapped to whatever physical addresses they're mapped to. And whenever we access an address, the memory management unit and the translation look-aside buffer will look at the tables, the entries in those tables, the frames in those entries, according to whatever page directory we have set within the CR3 register, which is a mouthful and is confusing, but that's how this works. It's like a table lookup structure whenever you access an address to see if it's valid and what flags are set and what user mode or kernel mode you're in, stuff like that. I'm going to have a variable for the current directory. It'll be a pointer. Call it current page directory. We'll just set it to null right now. And physical address will be current PD address, which I'll also set to 0. So the current address will be the physical address of the page directory, and that is what we are going to set within the CR3 register. We can't use a virtual address because after paging is enabled, that virtual address has to go to a valid physical address. We need a valid physical address to start with, which will be wherever our page directory is going to be pointing to effectively. But I have these separated out to make it better, and because that's how the tutorial did it that I followed. So okay, other than that, I'm going to have sort of helper functions within this file. Put this up here. I'm going to have a function that returns an entry for a page table, and it will be to get that entry within the page table. I'll also have one for page directory, which they will look pretty much the same, but contextually they'll be different, so I have them separated. So I'm going to take in a page table pointer, call it PT. So the way this makes it easier right now, since we have these set up as structs containing arrays, I can just set a pointer to a page table, which will have a pointer to a 1024 uint32 array. So it's a little easier to work with. And in this case, contextually, we'll be using, I'm using that word a lot, sorry. We'll be using a virtual address. I'm going to call it virtual address, which I have should be a uint32. Okay, so to get an entry in a page table, given a page table and an address, we want to look up what entry that address corresponds to. If we passed in something that isn't null, I'm going to return the address of the entry, which we're looking through that struct, and we're getting the entry corresponding to the index that that address corresponds to. Does that make sense? So I'm dereferencing a pointer to a uint32 array of 1024 entries, and the specific entry the address corresponds to is the index, which is shifted left by 12 to get rid of the flags and making sure it's within 0 to 1023. That goes to, the actual address that we're referencing here. Okay. Otherwise, it's not going to be valid. I'll just return 0, which will be for null, a null pointer, effectively. And I'm going to do the same thing for a PD entry. So really, I can just copy this stuff. And this will be PD. We'll return PD entries. We'll also use PT index for this though, which is kind of confusing. You think we'd use PD index, but we don't because I'm not using 4 megabyte pages, but it's fine. We'll use the PD index later. Just for this case, it's awkward, but since the pages I'm using both have the same frame setup, it's just everything that isn't the lowest 12 bits. We can use the same indexing macro to get the right entry for a given address. And I probably should comment my stuff, right? Get entry in page table, given address, page directory for given address. Okay. I'm going to have a function to return a page, a pointer to a page, for a given virtual address in the current page directory. So I'm going to get a page in the current page directory given a virtual address. Return a pointer to that page, so I don't need to do this, I guess. Self-explanatory by the function signature that I do. Like that. So I'm going to get a page given an address. I could make these things, constant. I probably should do that, right? Although if I make this, I think I can make these constant and be okay. Trying to go more slightly functional programming over time. I guess the compiler can optimize, hopefully. If not, I can at least see with my eyeballs that these things shouldn't be changing, so I don't have to worry about global state, all good things. But we're passing in a virtual address. I don't have anything for virtual address. I thought I did. Oh, I called it virtual. So this is a helper function that I made just because I'm doing in several different places, including in our malloc implementation later and in the kernel. I'm going to be wanting to get a page in the current page directory. So I just made this as a helper function. So I'm going to get, I should put get here, sort of like getters and setters, but I'm going to be getting a page directory, getting a page table in the directory, get page in the table, and then we'll return that page effectively. So sort of 3 to 4 step process here. But it just makes things easier later on and abstracted out stuff. So this is useful. So our page directory, I have a pointer to it will be whatever our current page directory is set. Right now we don't have one set, so it's pointing to 0. We will later when we set up paging. The page table within that directory, so our page table entry, first off, will be the address of the entry given the address. So we want to get the actual page directory index now, given the virtual address, which is going to be, I call these virtual address, yeah. Given the virtual address, this will be shifting it right by 22, which will work and give us the page directory index for that address, the page table pointing for that address effectively within the page directory. And then with that entry, we can get a page table, which I'm going to get a page table size pointer to the physical address. This is how it was spelled, I think. Physical address for that entry. So a pointer to that entry to the physical address. Struggling to know. I'm trying to think how to best explain these and not be worse than I'm already explaining. The table within the page directory will be at this entry, right? This is the entry within the page directory. The page table physically in memory is at this entry. So I'm getting a pointer to that address for this entry, because that's physically where the page table will be at. And I'm getting the page within that table as well. Hopefully that makes a little more sense. That's the motivation here. The page within that table is going to be an address to the entry within the page table of the index for the address. I'm getting the page table within the page directory. I'm getting the entry within that page table, all given this address. Okay, and then I'll just return the page. Return the page. Here I am. Badly typing again. Here I am. Up on the page. I'm going to allocate and not try to speak anymore. Yeah, sing rather. Allocate page. So I'm doing a void pointer for this. So what is this going to do? This is going to allocate a page given a page table entry. So if we're given an entry in a page table and we want to be able to use that, and it's new, it like hasn't been used before, it needs to point to a valid physical address in RAM, right? We have a virtual address, a page to work with, but it needs to point to a valid physical address. And I want that physical address to be allocated through our physical memory allocator that we made a while back, our physical memory manager, so that we say, okay, here's a new 4K block of memory, associate it with this page, and then the program can use it. I'm going to get a new 4K block of physical memory that hasn't been used yet. That's also why I included the physical memory manager here. I'm going to get a new physical block of memory by allocating uno block, which I could bring that up. Yeah, there it was. So I'm going to allocate one block, which will find the first free block and return the address to that. To one block. And I'm going to change this function a little bit later, because there's kind of a bug here that I didn't take into consideration. And also test block wasn't really working how I thought it would. So I might take this out or comment it out or something, but I will change this first free blocks function in a while. But anyway, we're allocating a new 4K chunk of memory, physical memory. And if we got one, then we want to map that in. So map page to block. So we're sending a page in, and we're basically asking for a new physical address of new memory for this virtual address, this page, to be mapped to. So when you use the virtual address for this page, it'll actually use whatever physical memory we just allocated. That's how the whole memory management unit and thing works. So given this page, I'm going to set the frame casting to a regular uint32, whatever new physical block of memory we just got. Okay. And then since we got a new physical block of memory, we have a new page effectively. I'm going to set it as present by setting that attribute. So I'm setting the address that we send, the address that we get, rather, from allocating a block of memory. I'm setting that within the frame by doing this, ORing it with the address. And then I'm setting that attribute of present, which all this does is set the first bit. So an easier way to do this would just be setting page equal to, ORed with the block and then set it to like 1 or something, right? Or I could just OR it with 1. I could just do this instead of doing this. This just kind of abstracts it out. And this would be more efficient as well. But the reason I'm doing it this way with the macros is just because it reads better in English. This is not a very efficient OS, keep in mind. So at the end, I'm going to return the block. If it's 0, it'll return null, right? But if we had 1, it'll return it pointing to this physical address. So that's good. To go along with allocating a page of memory, we'll also have something to free the page of memory, which is not going to return anything, but it'll do free page. Take in a page pointer. And this is going to get the void pointer. This is going to get the address to the actual physical address of the page that we send in. So the physical address is also just everything above the lowest 12 bits effectively. So I could do these a better way and not need so many macros. I could write these better, I think. Like a get frame instead of a set frame, which would be this. But again, this is just getting everything that isn't the lowest 12 bits for the address. In this context, it counts as the physical address, because when I'm freeing a page, when I'm freeing a physical 4K block of RAM, I'm freeing memory at a physical address in RAM. So that's why I'm saying this is the physical address for the page. Okay, and if there is an address there, and I'm going to free it by freeing the block associated with that physical address. It'll be one block, because one page associated with one block. One 4K block of RAM is one 4K page. Right, so that's why I'm doing this. 2, no, was it 3? Oh no, it's 11. I'm like, what buffer am I trying to look at? This one. 3 blocks. It's unsetting a bit effectively within our memory map, which is saying it's free for use now. That's how I'm freeing a block of memory. Okay, so once we freed the memory, we need to mark it as not present. So if we try to use it in the future, it'll generate a page fault. This might be like a use after free bug or something in the future. We want to catch those. So we're going to clear the attribute for the present flag, the present mask on the page. And again, what I could do is like that, I think would work. That would have a 0 for the first bit and with everything else. But, make it a little easier to read. I'll have it behind the macro here. Okay, I'll have function set the current page directory. We'll just have it to set the current page directory. Maybe I want to catch if it's true or false, if it actually worked. I set this as a bool. I don't think I ever checked the output of it though, but that's okay. We'll have it be a bool. We can check if it's true later. More likely I'm going to forget and never check, but I'll just say right now, I'll check it later. Page directory. My voice is dying. Sorry about that. I know I spent forever and a half going through these. That's why they take 3 hours long, but I'm not used to talking this much. I barely talk outside these videos, which is kind of sad, but I talk a little bit, a couple times a week to people, friends and stuff, and at work, but not for hours straight. So my voice dies. Apologies, because I'm not used to talking for hours at a time. Maybe I'll try streaming more in the future, and I will be better set for voice durability. But okay, if we passed in something that's bupkis, we don't want that. So we'll return, hey, that didn't work. Otherwise, whatever we set in, a pointer to a page directory that we want to set, I'm going to set that as a current page directory. This is a pointer. Right? Yeah, right here. It's a pointer. Okay. So also the reason I'm setting this up, one, initially to enable paging, we'll have to use this, but two, in the future for like multitasking for more than one process running at a time, or just loading a different program later, a process. I don't have processes yet, but later when I do, I think a relatively easy way to handle that for memory management and paging and things is to have a page directory, or at least page table, probably a whole directory per process. And we'll map the kernel into every directory for every process, so we can use syscalls and the kernel can still do its thing. But to set a different current directory for a process that is running, and then we switch between processes every so often for multitasking, right? We'll use this function, right? We'll set a new directory for a new process, so that that process can use different virtual addresses than another process. And it'll use those through a different page table, through a different page directory. So that's why I have this function here. Hopefully that is a decent explanation. But that won't be in this video, but it should be used for that later, I think. So the CR3 register, that is control register 3, holds the address of the current page directory. So, and I'm doing this in inside assembly. I've been saying that this whole video probably. Inline assembly. Sorry about that. AT&T syntax, always fun, but I'm going to move into EAX the CR3 value. Sorry, I'm going to move the value in EAX to the CR3 register. That's what I meant to say. Not going to return anything, but as input in EAX, or in A, I'm going to put the address, or since it's a pointer, I can just directly put into the accumulator this current page directory. Can't copy and paste. I don't know what I'm doing. There we go. Current page directory. We'll put that into EAX. That'll be the address to the current page directory, and that will go into CR3, which will set up that to be used for paging from this point on. So at the same time, doing this effectively invalidates everything in the translation look-aside buffer, and it'll be reloaded as we use pages and cache them and all. That also does this. So we could call this, if we wanted to, we could call this with the same page directory if we just wanted to invalidate everything within that page directory in the TLB. That would be another way of doing that, instead of one page at a time. But if we wanted to do one page at a time, for a good segue, we'll flush a single page from the TLB, have a function for that. Translation look-aside buffer should be the name. So flush TLB entry, and that will be given an address. So it will invalidate a page at a given 4 kilobyte aligned virtual address. That's what this does. I'll also use inline assembly for this. And I'll clear interrupts first, invalidate the page. I need to put a %, or well, I need to put this within parentheses for this to work and be correct in inline assembly. Then we'll set interrupts when we're done, no output, but as input, and whatever register I'm going to use, it doesn't matter, we'll put in that address. So at this address, we're going to invalidate the page at that address. So I think in Intel syntax, it would be like this, maybe? I don't know, but anyway. Okay, then we'll have functions for mapping and unmapping a page and enabling paging. Map a page. Have this be Boolean so we can return false if we're out of memory and we can't map anything, or if it fails for some reason. I'm going to have a physical address, which I called there. And I'm going to have a virtual address, which are both uint32s, but we're going to map a virtual address to a physical address or vice versa. And this says, you know, when we use a page, and that page representing a given virtual address, like 3 GB, if we access that address at runtime within a program, you know, we're going to look at whatever physical address is attached to that in the frame of the page table, of the page directory that is currently set. Just for, you know, recapping things as we go along. so that I understand it better. So hopefully you understand it better. I will be repeating a little bit of logic up here to get a page, just because we need to map in a new page table if it doesn't exist in the middle of this. So that's why I'm doing these again, not to repeat myself in code for no reason. But current page directory, we want a page table, which will be an entry in the page directory, which will be the PD index of the virtual address, which I could call it uint32. Oh yeah, because I'm passing in a void pointer. It could be either. I could make these uint32s instead of void, but I guess maybe later this would work easier for things. I don't know. But since they're void pointer, I gotta cast it to a regular value. I didn't need to do that. I'm making this harder than it needs to be, but that is all right. If that entry exists and it is present and accounted for, so basically if the entry and present equals present, so if the first bit is set, effectively is what I'm doing here. I could do test attribute because I did make that function, but I didn't do that, so maybe I can do that later. Use test attribute for this check. All right. If the page table, if the page directory entry is not present, then we need to make it present. And I'm assuming at this point, if it's not present, then it hasn't been allocated. We don't have memory for it set, so we need to allocate memory, get a new page table, and set it as present. So that's what this is for. Page table not present, allocate it. Page table. I want a pointer to a new block of memory, a new 4K block of memory, and each page table will take up 4K of space because it's 1024 times 32 bits. 1024 times 4 bytes, which is 4096. So convenient, right? One block is enough for one page table. And we'll get a page table pointer to a block that we allocate. If we can't allocate a block, then I'll return false. We're out of memory. If I can allocate a block, then I'm going to clear that memory in case it had been used before. Call memset that I have on the table, 0. We do size. Yeah, we can use size of page table, I believe. Yeah, with size of, I can use parentheses here because I'm asking for the type. You know, this is a type. That'll set 1024 times 4 to 0. So 4096 bytes of zeros here. And I don't have that up here. And I don't need to do this anymore because I put that thing in the makefile. But I need it here. That is in string.h. Do have memset, right? Yeah, I have memset because I use that. That's down. That's right here. Here's my simple memset. It kind of works. So, you know, not efficient, byte-wise at a time, but it works. So we'll make a new entry in the page directory for this page table because we're mapping a new page. We need a new entry for that. Actually, we just allocated a new page table, so I need a new entry for that. That's what I'm doing here. So I need the address of the entry associated in the page directory, so at the page directory index of whatever virtual address we're using that's been passed in. And I'll finish the sentence. After we make the new entry for it, we'll map that table in, and we'll enable attributes here. I'm going to set that entry as present in the page directory, and I'll set it as writable. Yeah, read write. And I'll set the frame, I'll set the address, physical address for that entry for that table. Okay. So setting it as present and read write, and again, what I could do instead of these is just setting this to like 2. That would do the same thing here, but no, present would be the first bit. Set it to 3. That would be the same thing as doing these, but again, to read easier. And then we're setting the physical address of the table that we allocated for that virtual address. We're mapping it to a physical address in the page directory. So that's what we're doing here. Okay, and after we do that, if we didn't do this, we still have to get the table, so this is redundant in this case here. But if this didn't happen, we would have to get the page table. Okay, page table is a pointer to the physical address for the entry. So this is for the directory entry up here. That is what table we're getting. But we're getting a pointer to that entry, so we can fill in a specific entry within that table. This gets the whole table. We need an entry within that table. That's why I'm getting a separate pointer here. So we want the page in that table. Okay, so PT entry page, pointer to uint32 value, located at this table. Since it's a page table, dereference, get the entry for the page table index. Again, for the given virtual address. There is a bit of boilerplate in my code, I realize. But hopefully it makes sense and it's simple enough. Simple doesn't mean easy. Those are two separate concepts, but I'm hoping it's simple enough to follow. Also keep in mind, if this isn't simple, I also spent about a month, I mean not every day, but a few hours, or at least a few days during the week, for I don't know, 3, 4, 5 weeks to get through this and refactor and refine and, do things. So I didn't do all this in one day. I don't expect it to be super easy to follow, but I'm hoping it's relatively easy to follow. Okay. After we get the page within the table, we need to map in the page, because that's what ultimately we're doing here, mapping a virtual to a physical address. So I want to set the frame of the physical address that we sent in to the page. So we're getting the entry within the page table. We're setting the address for that entry, which is going to be the actual physical address of RAM that we refer to when we use the virtual address that is this page, right? So if in a program we use address 20,000, after we enable paging, the processor is going to say 20,000, that's a virtual address. What actual address does that correspond to? And it'll go through and get the frame or the physical address associated with that virtual address. It'll say, okay, 20,000 virtual address is actually 35,000 in physical RAM. And it has the flags of present and read write, so you can write to it, so you're all good to go. And if not, it'll say, oh, I had an error, we'll throw an exception, or something. That's why we need to map these virtual to physical addresses. Okay. And I'm also going to set the present flag, or else we'll have an exception because it won't be present. So yeah, make sure you set it present. I can do that first, it doesn't matter because these are just ORing values. Okay, and if we've mapped successfully, I'll return true, and we'll be good to go. As the contrast to mapping a page will also unmap a page. Given an address, given a virtual address. I guess I shouldn't call these the same name as the types, so maybe I'll do that vert. I didn't think of that, because the types I have are physical and virtual. Go up here, grab everything. Down here. Change virtual to vert. Okay, easy enough. So vert address. We'll get a page. That's why I have that helper function up above. Oh, it's going to come in handy. Get rid of that highlighting. Get a page for an address. That's what I'm going to do here. uint32t vert. Yeah, so given the virtual address, get the page associated with that address, which will be within the current page directory. For that page, I'm going to set the frame to 0. Effectively, the virtual address points to null physically. So if we try to access it, that'll be a no-no. That'll be out of bounds. We won't want to do that. This won't affect anything because we're not using it like such, but if we have a better malloc implementation or something in the future, we can say, you know, accessing physical address in RAM, accessing 0, dereferencing a null pointer, if you will be bad, and we can throw errors and stuff. I don't have stuff set up for that, but anyway, it's something that could be a part of that process. So I want to say effectively, this is now a null pointer for this virtual address, in a way. Maybe that makes it more confusing, I don't know. But also, if we unmap a page, I want to set it as not present. So I'm going to clear the present flag. And that means if we try to access an address, accessing a page, after we unmapped it, will trigger a page fault exception because we're accessing a non-present page. That is not present. Trigger a page fault. So #pf is the nomenclature for that exception. One more function in this file before I take a break. And then it's the end of this file anyway. But similar to having a function to initialize the physical memory manager, I'm going to have one to initialize the virtual memory manager. And I'll have bool in case we're out of memory and we can't do it, or something goes wrong. I guess I'll try to capture that somehow. Initialize virtual memory manager void. So I'm going to create a default. This is before anything else is loaded. This is not setting up a different page directory for a loaded process. This is to start everything off and enable paging and everything. I'll make a default page directory. Called dir. Default page directory. I'm going to get a pointer to memory to a block. For some reason, the brokenthorn tutorial used 3 blocks. I don't know why. Each page directory is going to take up 1 block of space, but they allocated more than 1 block. I'm not sure why. I don't know if I have to do, if I can, you know, go with 1 or 2 or 3 or whatever. It might be to allocate other stuff in case I want to put more directories behind it or something. I don't know. 3 worked, so I'm going to do 3. I'm not sure why I'm doing this, but anyway. That's a good explanation, right? I don't know why I'm doing this. I'm just doing this, but oh well, it works. So if we don't get 3 blocks, return false. Couldn't allocate that. We're out of memory. Otherwise, we'll clear the page directory. Set as current. I'm going to go a little bit off from what I did before and just use memset, because I think that makes more sense. At directory, we'll set zeros for the size of page directory. Okay. So then for everything within that directory, to go with the word size of my machine, for everything, every entry within that directory, I'm going to set as present. So you can do it one of 2 ways. You can directly set it to like 2, and that'll set the present flag. Or we could do, you know, set attribute, set the present flag. But for this, I'm gonna do this. So that'll set it as supervisor, which is bit 3. Readable, writable, which is bit 2, and not present, which is bit 1. That's just a default, setting readable, writable things. Then we'll get a default page table. Table pointer, allocate blocks. I'm going to allocate another block for a page table, although I allocated 3 up here, so I might be following bad tutorials, but okay. And again, if we don't have it, we're out of memory. I'm going to do this twice, actually. So I'm going to do effectively a higher half kernel, which means for the physical address that the kernel is at, I am going to memory map the first 4 megabytes as well, but for where the kernel is at, I'm also going to include the kernel at virtual address 3 gigabytes and above, which is like C and the rest zeros, right? That way, when I load programs and processes and do stuff later, I can have those start at like 0. They can reference virtual address 0 or whatever, and they can use up to 2 gigs or maybe up to 3 gigs, and the kernel's way out of the way. And most programs don't need to use that much RAM regardless, but this is basically for a higher half kernel. I'm going to have a separate page table that refers to addresses 3 gig and above, and I'm going to put the kernel and its stuff also at 3 gig and above, so using a higher half kernel. But the default, I'm calling a default page table, is going to be just for regular addresses. I could call this table 3 gig, table 3G. We're not even 4G yet in this OS. We're still at 3G, decade-old technology. Not return false. Okay, I want to clear those page tables. So I'm just going to memset them. Again, make sure the memory's good and free. If I had a calloc function, maybe I could use that, but then again, I'm going to build malloc on top of paging, so I probably couldn't use that at this point, so never mind. We'll just memset it to 0. So I'm going to identity map the first 4 meg of memory, the first page table, virtual addresses, and physical addresses, 0 to 4 megabytes. So mapping the same virtual to the same physical address, identity map. I'm going to do that. And I'm also going to map the kernel to the 3 gig space, but I'm going to have 2 for loops that look basically the same. I'm just letting you know that first. Map kernel to 3 gig plus addresses. I think that means higher half kernel. But okay, so I'm going to have, a thing here. I'm going to have an address for the current frame and an address for a virtual address to map to that frame, which is also going to be 0. While I is less than 1024, so every entry within the page table will increment I. Frame will be incremented by the page size, as well as our virtual address will be incremented by the page size. I have that. Right? Yeah, page size. 4096. Okay. Or 1000 in hex. So for each entry within the page table, I want to make a new page, which just means setting a 32-bit value to 0. Effectively creates a new page out of the other, right? I'm going to set that page as present. And it takes a pointer, so we get the address to that. For my purposes, I'm going to set them as readable and writable for the kernel to use as it pleases. And then I'm going to set the address in that page, so setting the frame, the physical address for that page for the frame. So this will set the virtual address 0 to the physical address 0, because the first entry in the page table is going to be this one right here, and then we'll go through all the other entries. How do I put it in the table? I'm identity mapping the first 4 megs of memory, but I'm going to put it within the page table allocated for the 3 gig space for the kernel to use, so that the higher half kernel can use the initial, everything we have set up in the first 4 megs. So stuff looks a little wacky. It kind of seems reversed. But we're adding the first 4 meg of memory I'm adding to the 3 gig page table. The kernel mapped to the 3 gig addresses is going to be mapped into our default page table that I called up here. This one. So yeah, it's kind of confusing. Sorry about that. I don't follow the best tutorials, so I don't say the best things, but in our 3 gig page table, I'll put this new page. So the index, the valve index for our virtual address is going to be this page. Simple enough. Since I made it a regular uint32 value and not a pointer, we just set it equal right here. So this page, the page will be, deallocated from the loop, but the page table will not, because it actually points to a physical address up here. And that physical address will hold 32-bit values corresponding to these pages of memory that have been identity mapped and put into the table. Okay, so I'm going to do something pretty much the same. I could have done these both in one loop, but it helped me to understand. Have them in two separate ones, as well as the thing that I followed had it as two separate ones. So this one, I'm going to set the frame equal to whatever address we have the kernel at, which I don't think I have that set. Thought I had a global, yeah, there we go. Yeah, I don't have that set, so I'm going to define in our global addresses here a kernel address, kernel area, which right now it's at 50,000. I do want to move this to 100,000 in hex, or 1 megabyte, because the physical memory, how it's laid out, at least on my hardware, on my laptop, I have the huge amount of free space, basically starts at 1 megabyte, or 100,000 in hex, and then it's free up until the limit. So I'm gonna move this probably within the second stage bootloader to 100,000 later, but right now it's at 50,000, so I'm just gonna do that. Which also means I need it up here. I'll just have it here. Global / global addresses.h, is that what it's called? Okay. So the kernel address will be mapped to virtual address starting at 3 gig. So C0 and 1, 2, 3 more bytes. That's 3 gigabytes. And then we'll do the same, increment by 4096 bytes each time for each page, for each frame. Set it as present, readable, writable, put it in the frame, except this table will just be the default table. The lowest addresses will go to the 3 gig space. The kernel is being mapped to the 3 gig space within the lowest addresses. That way, the kernel is kind of mapped within both. And when we refer to, kernel can refer to things above 3 gigs or whatnot, and it'll be fine. So I'm not good at explaining this. Other articles on the web are better at explaining this, but this makes a higher half kernel. The kernel is mapped simultaneously with this first identity mapped 4 megs and also at 3 gigs. So that process is loaded from the kernel, can refer to addresses below 3 gigs and be fine, because the kernel's going to be within those processes later anyway. But it'll be high up in memory. It won't overrun anything. It's safely out of the way, and it's higher half of RAM. And it's called higher half because 3 to 4 gig out of 4 gig is the higher half. 0 to 2 gig, or well, 1 to 2 gig, whatever, is sort of the lower half of memory. I think that's why it's called higher half, but regardless, that maps the kernel. So after that, I'm going to get the page table within the page directory that refers to the 3 gigabyte address. So PD index of that. I'm going to set the 3 gigabyte address table, page table, as present. So set attributes entry PDE present. And I'll set it as readable and writable. And the physical address for that table, for the higher half kernel table, is going to be the default table for the low memory. So physical address table. So this table here, this block that we allocated for this low 4 meg identity map memory, well, for the kernel being mapped here to 3 gig in this table, that is being referred to within the page directory as the entry for the 3 gigabyte virtual address. So when we refer to a 3 gig plus address for the kernel, it'll be physically pointing to the table here that we set those addresses to be at. I'm not good at explaining, I'm sorry, but that's what we're doing here. And then I'm doing a similar thing. I can just copy this. It's called entry 2 or whatever. This will be for 0, the low memory. I'm going to map into the 3 gig table. The 3 gig directory entry points to default page table. I'm going to have them point to each other effectively. Default directory entry points to 3 gig page table. And that's kind of what makes this work. They're kind of referring to each other. So the kernel is mapped in 2 places at once, right? But it works. Except this is entry 2. I think that is all right. All right, we set up a current page directory and identity map the first 4 megs and set the kernel to be higher half. We want to store that page directory now that we just set up. I don't know what I called this. Current PD address. That's what I called it. So that is going to be a physical address, which again is just a uint32, but contextually this makes better sense here. Physical address, directory entries. So the array within the struct, the array of entries, we can get an address just to the start of that array, and that is the actual physical address, because, you know, when we compile this, it'll be put at an address, it'll be put into memory. So that is where we're going to set this. That is where the current page directory is at. This might also be, we might could just set it equal to directory and this would be the same. But I guess I did it like this because I'm sort of saying we're pointing to all the entries within the directory and that's where it technically starts. I don't know. I think those might be the same, but whatever. Okay, so after we store that within a value, a variable, we want to set that or switch to that page directory, set it as active. So we'll set the page directory. Which will move it into CR3. So our CR3 register points to the current page directory. Am I using this address anywhere? I'm not using this anywhere. I just realized that. Oh yeah, I don't even need that. Wow. That's an unused variable. I don't even need to do that. Okay, well, we'll get rid of that. Not even using it. Am I using it within the current? No, I'm not, because I just did a check. Okay. Let me do a find here. Yeah, I don't need that. So that's good. I'm changing my stuff on the fly. Hopefully it doesn't break anything. I guess I did simplify this over time, so I guess I just didn't get rid of that unused reference and stuff. It wasn't an unused reference because I was setting the value, but I never used that value anywhere. So anyway, that's cool. Yeah, that's all right. We'll switch to the page directory by doing this, which will set it within our CR3 register. And then we'll enable paging. Actually enable it, which I could have made a separate helper function, but I only do it once here, so I just have it set here. We're going to set the page bit, so PG, paging bit, which is bit 31. And PE, which is, I don't need to set, but I'll do it again for completion's sake. Protection, enable bits 0, paging bit 31 and PG bit 0 of control register 0. And that effectively enables paging. So from this point on, any address you refer to is treated as a virtual address. So in all likelihood, if I initialize virtual memory without changing how things are set up within the kernel, I'll probably just get a page fault by default, and that won't be great. So I will set up a handler to catch that, right after this, before I make other changes to actually use paging within the new kernel and programs. But into CR0, I'm going to move EAX. Could make these double parenthesized. I guess I don't need double. I'm not referring to other parameters in this inline assembly. So I'm going to OR our EAX value, our original CR0 value, I'm going to OR with bit 31 and bit 0 to enable paging, protection enable, which PE was already enabled when we moved to protected mode. When I OR'd just 1 in CR0, but set it here anyway. All right, so this is PE. This is the top bit of the 32-bit value, paging. So that's going to be EAX. We're ORing that with. And I'm going to move EAX back into CR0, which enables paging. And then we're good to go. If we got to this point, then we initialized virtual memory, and we're good. Okay. It's not too bad. It's not too big. 257 lines. That's not bad. I put in some more comments and spaces than I did in my diff, so it's slightly longer, but that should be all we need, assuming I didn't mess anything up, which obviously I did because it doesn't compile. That's all right. Oh, constant. Oh, I can't return a constant address. That's why I didn't have constants. Okay, well, that's why I want to not do this then. I wondered why I didn't have those. I can't return a constant reference because it gets rid of the const. I can return it. It's kind of like, why are you doing that? Expected expression. Expanded from PD index. Did I not do that right? Is that line 89? Okay. Here. Entry is page directory. Entries. PD underscore index. Given our virtual address. Oh, because I called it virtual address because I'm a big dummy. That's the type. I'm sending an address. I probably did that in a few places. If you saw that, then I'm going to have to, fix these mistakes here. 159. At least my kernel catches my mistakes. That's always good. Equals. Set frame, invalid operands, unsigned int, and void pointer. Ooh. Ooh. Unsigned int and void pointer. This. Oh, sorry. Physical address is the variable, but it's also the type. Yeah, this needs to be, I'll call it like phys for physical address. And then where we actually set that, I did call this phys address anyway. I just didn't put it up here. That's all right. That is all right. PT entry identifier. You don't like that? PT entry. No, I'm just page. PT entry page, because that's what I'm referencing. And I did the same thing down here because I just copied it. Oh, there we go. Look at that. Not too many errors. Okay, not too many bad things. I'm gonna take a break because I've been recording for a long time and my voice is dying. I need to like eat and get water, and this is probably already like 2.5 hours, so that's great. I'm gonna be back in a bit, and I will make the just print to the screen error for the page fault handler, and then we'll go from there. All right, let's continue on. I'm gonna write the small exception, number 14, for the page faults. So we have something that shows up on the screen in event of error. And I'm just gonna write to the screen probably the error code that we got and the faulty address, since a page fault address will, in the exception handler on the stack, the register CR2, control register 2, will contain the address that caused the page fault. So that's pretty handy. So you can use that later on to like say, okay, was this address supposed to be valid? Then we'll take a page for that address from the disk and swap it in and go back to the calling process to handle after we handle the page fault, and we're good to go. So stuff like that. But I'm going to just write that in just to print stuff to the screen. So we're not really going to do much, but this will be good for debugging. For debugging purposes, we have this here. We'll do something similar. Paste. There we go. Oh, what did I call it? Oh, page fault handler. Yeah, I was very, very creative with my names. Yeah, page fault handler. This one also has an error code though, so constant 4 bytes error code for this. Okay, and we're just gonna write red to the screen. This will also have an address. It'll say this is the bad address. Instead of divide by 0, I'm gonna put page fault exception hash pf or pound or octothorpe, probably other names for that. Go carriage return line feed. I'm going to write the error code down. I actually want that at the front. Okay, so the error code will be whatever error code we get. Need to learn better Vim keys, so let's do change to double quote. I don't want to get rid of it, but okay. Error code will be the error code passed on the stack, which for my purposes for this will probably, the error code will probably just be 0 or 2, reading or writing a non-present page. So 0 for reading and 2 for writing, I think. Those should be the only error codes that show up, but you know, maybe something else will. Delete that, so that'll be at the end. CR2 contains bad address that caused page fault. So the virtual address that the memory management unit looked at to get the right physical address, either this page wasn't present, a virtual address corresponded to a page that was not present, or some other error occurred. The address that caused this for that page is going to be in CR2. So I'll just print that address to the screen, because I can use this for debugging, like if this address is for the frame buffer, say, then I'll be like, oh yeah, I forgot to map in the frame buffer. That's why that doesn't work. Or if it's for 20,000, I'll say, oh, I didn't properly map in a page to load a file in the editor, you know, or something. So it can help with debugging things, if you know what the address corresponds to. If it's just some random address, it might correspond to some faulty pointer somewhere, or use after free if you have a malloc free or something, you know. Sometimes it's hard to figure out, sometimes it makes more sense, but we'll see. So CR2, I'm going to move into, as output, I'm going to override a register, and that register will have, well, will point to the value for bad address. So into our variable here, I'm going to put the value in CR2, which will be the address that caused this page fault. Just as outputs. So we have the error code. And I'm just going to write the address. And this will be bad address. Simple enough. For debugging, I'm just going to probably just halt. I want a better implementation, but right now this is just for debugging. So ideally, we won't get any page faults. The only page faults that occur for this video are going to be if I mess something up. So I'm not going to handle them and swap in correct pages from this. That'll be later when I'm sure that that is the only reason these are happening. Right now, these shouldn't happen unless I didn't implement needed functions or something, right? So let's put it to do. Replace with actual. Implementations for mapping in and setting present. Read, write, etc. Pages. Okay. Right now, I'm just going to do CLI and halt. But okay, it should write on the screen error code, give the error code, and give the address. So that'll be good. We don't have anything set up for that now, though. I should make sure it compiles first, right? Okay. But we can add that in. This doesn't happen anymore. I can get rid of that to do. That's good. Wherever I'm adding these things in, the exception handlers. These lines are kind of self-explanatory. I don't think I need these. I thought about that. And debugging, I can add them in later because I know where they're at. But okay, this is exception 14. I'm going to put 14. Page fault handler. I believe it should still have trap gate flags. Yeah, still has trap gate flags. So instead of divide by 0 error, this will be page fault pf errors. I think divide errors are -de for divide error. I'm not sure. I can change that later, but and I didn't mess anything up with that. Okay. So I also want to move around how this is laid out before we get user input. Since I'm setting the foreground and background color and I'm printing out stuff in between setting interrupts and everything, and that's fine. I thought about this, and I think to make a little bit more sense, I should do all of the exception and interrupt setup and the hardware setup, drivers and everything, checking what the user has installed for devices and all, before I do this sort of user mode stuff and go into the shell. I think I should, do the hardware and interrupt setup and everything first, and then we can see if there's any bad things there and fix them up before we do, printing to the screen. So probably going to move around some logic here, not too much though. Later on we will need pages, so while I'm here, I'm just going to add a needed pages thing right there. But our initial setup, I'm going to change this to initial hardware, interrupts, etc. setup. And we'll set up interrupts first. Yeah, this. And the exception handlers and the software interrupts. I'm going to move this up here first. I'm going to pick stuff here. Pick the descriptors, getting the PS2 keyboard, masks, enable RTC. Let's put that here. I had an issue on hardware where you saw at the beginning of the video, among other bugs, the date time was showing up. It was not respecting that I have show date time set to false, as a static var in the pic.h file, I think. So I'm just going to set that here first before we enable the clock. I'm going to say, hey, I don't want you to show that, even though that's how it should already be set up. That's all right. I'm just setting it false explicitly. Don't show date time on boot. Although it may be useful to show that, but if you type in show date time at the shell, it will, show it. So I just don't want it to show up on boot because I didn't tell it to. And it does it on hardware, but not in emulation. For whatever reason. I'm going to set the frequency before setting the interrupts, and I'm going to move this stuff as well up here. So all the hardware stuff should be taken care of, and interrupts, and then we can do setting the colors and stuff. Yeah, I think that makes sense. I'll do that. I had like a debug string. Yeah, this, I don't know why I left that in there. Get rid of that. So even though it'll probably error things out, I'm going to go ahead and put in, to enable paging and stuff in here. And see what happens. See if we get any page fault errors, stuff like that. So I set up the physical memory. So after I do that, I'm not going to print this out. You can do that with your own command to print the memory info. So I'm going to get rid of that, keep this simpler. Where am I printing the... I probably got rid of it. I was like, where am I printing the boot message? Menu stream. I got rid of that, didn't I? Oh, no, there it is. Where's this happening? Oh, that's before when we're setting colors. No, I want to do this like last. I want to do that last. I'll do that right before we show the shell. Okay. So at this point, we set up the interrupts. Hopefully we set up other hardware in the future. We set up the physical memory manager. Our usable blocks are not usable blocks. So after we've set up the physical memory manager, we'll set up virtual memory. Set up virtual memory and paging. Do I have set up physical memory? Oh yeah, I have here. Let's do set up physical memory manager. Okay. So we'll initialize, which I don't have it open in a buffer, it's okay. Initialize virtual memory manager. Which I think took a bool, so I should probably check if it's yes or no. True or false. I'm not doing that right now, assuming it'll just work. When it's set up, we will probably immediately get a page fault for accessing the frame buffer when we try to write to it down here. I guess I can check that right now though. Since I have the exception set up, I don't know if it'll write it to the screen because we don't have the frame buffer set up. We'll find out. What happens? Nothing, it triple faults. Oh, that's good. That's always good. That's okay. Let me map the frame buffer in so maybe we can print stuff to the screen. That would be good. Although I guess before I do that, I can check if we actually get to this point. Job is never done. Okay. As input, let's just move some value into EAX so we can check we got here. We'll do 777s. Because printf debugging is the way to go, and it halted so we know we got to this point, right? We can do that, or you can print the registers, but yeah, it's 777, okay. So we know we're here, and I think it's to do with writing to the frame buffer, which is not good. Actually, I can check that, well, I can't print to the screen until we have valid pages mapped for the frame buffer, because it's at some high area in memory. That isn't marked as present, that isn't mapped in. So I'm going to identity map the frame buffer, so that we can write to it and refer to the physical base pointer, which is, you know, what we use to draw string to the screen and pixels and everything. So right now, down here where it's trying to write to the screen, or even just clear the screen, or maybe even set some of these, depending where these are in memory, it's saying, hey, that's not good. It's trying to fault. I'm not handling the fault. So it's going to a double and a triple fault. And it's, yeah, messy. Identity map, the VBE frame buffer. So we can get some stuff on the screen again. So I had a constant here. Frame buffer size and bytes. I think I might move towards having stuff in the middle instead of everything, you know, up here like it's C89. It depends. In this case, I'm only using this in like one spot, so it's okay, but I don't know. It is less consistent just having crap in the middle here. Variables and all, but that's yak shaving, so who cares? We want to take a little off the top. We don't want to make the yak bald. Not yet. Well, the Y resolution multiplied by the bytes per scan line. We're in a linear frame buffer mode, so linear bytes per scan line will give us the frame buffer size in bytes. And then this will be mutable. I'll get the size in pages, which is going to be the size in bytes, divided by page size, which is 4096, but we'll just do that. And if the size in pages modulo page size is not equal to 0, is greater than 0, then we'll have an extra page. Although on my laptop, I had some issues with some of the frame buffer addresses still not working. And I think it was trying to draw like beyond like the end of the frame buffer that wasn't mapped in. And I know in QEMU, in this emulator, I've checked in the past, I don't remember how I did it, but I checked in the past how big the frame buffer was for QEMU and stuff, and it was like double. It had like two buffers, one behind the other. But where I'm going with that is I'm going to double the amount of pages that we need, if that makes sense. So whatever the size of the frame buffer is, I'm going to double that, just in case hardware behaves sort of like this, where it kind of has more than one buffer behind the main one, and writing to that would normally cause a page fault. This seemed to fix some bugs I had on the laptop. I don't know if it's the correct way to go about it, or if it's right, but it seemed to fix at least one bug, so that's what I'm going to do here. I might want to look into it later, but I'll put this for hardware, double size of frame buffer pages, just in case. But whatever size we get for the frame buffer, I'm just going to multiply by 2. Size in pages, not bytes. Well, either way would work, but ideally we would want the actual size in pages and not a doubling. But I can do that later when I find out how to actually get that. But alrighty, so I'll have a loop here to map in all these pages. So I is 0, the start of the frame buffer I'm going to use is going to be wherever the physical pointer is. So physical, well, I don't have it in physical base pointer, is what it's called. And until we're less than the size in pages for I, we're going to map in all the pages. I++, we're going to increment the frame buffer addresses that we're mapping, identity mapping, by page size, because we're mapping in pages at a time. Okay. And for each one of those, we're going to use our new map page function, which will take in a physical and a virtual address. So the physical address, I mean both void pointer as well. Take in a void pointer, yeah, to wherever we're starting, to wherever we're going to. So we're identity mapping. So each virtual address will be the same for the physical address. So we just put in the same address here. We're mapping the virtual address to its physical address counterpart by doing this. So that's for the frame buffer, so we can write stuff to the screen. And hopefully it works. I'll see if that works right now. Hopefully. It might not. No, it doesn't. We have an error. Well, at least we can see. We know that the frame buffer mapping worked. Beyond that, we know we're messing up somewhere because I have page faults. But I know mapping in the frame buffer worked because I'm writing to the screen. You know, these strings. I'm using print string and print hex. So I'm accessing a non-present page for address 430,000. So hey, page fault works. That's good. What did I do after that? Marked it as in use. Okay, let's do that. Mark. Frame buffer as in use for physical memory manager. That way we don't write anything that uses a virtual address, or well, virtual is fine. We don't write anything that uses a physical address for the frame buffer. So deinitialize memory region. For the physical base pointer, how many bytes are we deinitializing? The size in pages. You can do it another way, but I'll take the number of pages times the block size, which is the same as the page size. So, but I guess in this case we can use block size because it's the physical memory manager. Makes a little bit more sense. They're both 4096, but the number of pages times 4K is the number of bytes that the frame buffer takes up. So I'm just going to, mark those as in use. So we aren't going to allocate any blocks that have already been used for the frame buffer. Otherwise we'd have bad issues later. Then we'll set the colors, clear the screen, print the boot message, but this stuff doesn't work, as you just saw. I have some iffy addresses here at 430,000. I can see if it's frame buffer related by doing some different thing, and it does look to be frame buffer related for 1080p at least, because this works at 800 by 600. So that's interesting. 430,000. I wonder what would be using that address, because that's right after 4 meg, right? I identity mapped 4 meg. So what is being used after that point? I'm not sure at the moment. Something. But we know this works, but just not for what we want it to work for. And yeah, I have less blocks because I'm allocating the frame buffer now. But that is all right. Stuff still works, I think. Since we identity map things, even though I have a hard-coded address for loading programs to, those have been identity mapped. So it's still going to that address from that same virtual address. But we freed the address, so that's good. There was one issue I saw with loading things. Yeah, I can't load the file table, even though that's valid. That's a small bug I can fix right quick, that I remembered that. And then we can go to fix the other stuff. Okay, so that would be in disk. It'll be in check file name right here. I think one thing I did is just make this constant, even though we won't really need to use this in the near future when I actually write this to be slightly better, but right now we do. And 1000 is, this shouldn't be hard-coded, but it still is. For some reason I renamed this to pointer and not file pointer. I guess because I'm using file pointer in the editor. This is just naming, this doesn't matter, but So the issue with not being able to load the file table is because of this line, I think. Wait, no, I less than length equals 5. Yeah, this line. So we're using 0-based indexing, not 1-based indexing. So if I is the file name length, I is 10, we would have checked 0 through 9. We would have already checked the maximum length, which is 10 characters. And this would just mean it's, you know, we're on bin in the file table at this point, right? We're past the name. But this here, where I plus 1 would equal space, is not going to happen if it's less than 10. It needs to be I, not I plus 1. Because if we type in the full name file table, you know, pointer would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. The length, I guess, would be 8. But pointer 8 would be like the last one, and then pointer 9. And it's an off by 1 error, which is everyone's favorite thing in C, right? And the fix is just to use pointer I and not pointer I plus 1. Otherwise, we were looking past where we needed to be looking, and it wasn't a space, or it just wasn't correct. But that is like that issue right there. So that'll fix some errors with, you know, finding files. Allocated a block. See, now it works. Now we're still getting page faults to 430, but we are finding the right file. Let me see if that works for the 800 by 600 again. Because now I'm curious what stuff works and what doesn't until I fix. I did 16 bits. Oh, we can use the calculator. And we can load the file table. That's interesting. But I'm loading to 430,000. So that was another bug. That was with getting the first free blocks and everything from the physical memory manager. Oh, one thing I thought changed as well. Before I go to the physical memory manager, I'm going to change the linker scripts. Hopefully this works and doesn't break anything just yet, but I never had actual data. And in a file loaded like with the ELF file format or PE or other things, they tend to go text and then data and then RO data and then BSS, I think. Or it might be BSS and then RO and then data, but whatever. After all these things, it's, you know, the heap and then the stack, and the heap grows up, stack grows down until they meet and everything breaks. But, you know, at least had explicit data section, I believe, after the text section. So I'm going to add that to these linker scripts just in case. It was something that I added while testing, and it seemed to, I don't think it broke anything, but it didn't fix anything. Or well, maybe it did. It seemed needed. It's lacking. And I have mutable data, so I need actual data sections. Snake run. Yeah, let's go with this. Oh yeah, it doesn't work. The only thing that works is 800 by 600. Beautiful, but yeah, this works now. This works. I can write stuff and do it, so we're good. Okay. All right, we'll look at. So physical memory manager, this test block was not working. Or maybe it was, I don't know, but I found some bugs here with find first free blocks that weren't lining up with where I thought it should. I think it was because if I find, at least in some cases, if I find a bit that is free at the end of one of these 32-bit chunks, then I'm not checking beyond this 32-bit chunk. So if there's something like, you know, this one at the top is free, and there's stuff after this in memory that's free, then this does not check beyond this, right? It only checks if something's free here and then goes to the next one. But what if I wanted to, you know, check between chunks? What if there's 3 bits at the start of the next 4 bytes, and there's bits at the end of this 4 bytes? I want those to be connected together for an accurate count of free blocks, and that's not what this currently does. I want to kind of fix that. I don't remember exactly why test block wasn't working, but I don't think this is working either, to be honest with you. And it's only ever used in here. There was one reason it wasn't working, and it might have been because stuff could cross, you know, chunks. But for, I think set and unset work. It's just I'm not sure test works. I also made these constant because I'm on a constant crusade. Const. This can be const as well. I got a cat that's staring at me. What did I change in here? I think I did this. I just put free blocks into here because I could, because this is the only place it's being used anyway. Free blocks equals 0. Let's do less than. It might have been because I did count equal to num blocks, and that was counting one extra every time. That could be it as well. Okay, I did if. So to get the case that we are crossing over a 4-byte chunk into the next one to check if there's any free bits. If our bit that we initially check with, plus whatever count that we're on, counting the number of free blocks, if it's greater than 31, then we're going into the 4-byte block right after this one, right? So if it equals 31 and we're at the end of here, but we're going checking beyond the end, that's what this case is handling. If this plus the current count is greater than 31, greater than our current block going into the next one. So if we're greater than that and I plus 1, if we're not at the end of memory, is what I'm checking here, it's less than or equal max blocks over 32, then we can keep checking the next block of memory. So in that case, if memory map I plus 1, and I is up here, so I plus 1 would be the block right after the current one that we're checking. So if the 32 bits after our current one, I plus 1. If the current bit, in the 32-bit chunk after the current one is free, then it will be, we're checking if the bit is set. So if I do a not here, checking if the bit is not set. But it'd be 1 shift left by j plus count. A little bit of awkward arithmetic here that I didn't need to do this complicated, but 3, 4. Remap. Didn't need that one. So if memory map ended with 1 shift left by j plus the count minus 32. Okay, so if that bit's not set, then we're free. We'll increment free blocks plus plus. So this is checking if a bit is set in the 32 bits after the one we're currently in. In case we're at the end of our current one and we're checking into the next one. So if that bit is free, we want to add to it. Otherwise, we're only checking in our current, 32 bits. So else, and my logic within here is doing the test block logic, but a little better, that it actually works. Else, if not memory map I, so I plus 1 is the 32 bits after our current block. In this case, we're not past it, so we're still in our current block. So similarly to that above. If 1 shift left by j plus count. Free blocks. Now, I mean, I could do this and this or this, right? That would be equivalent because I'm setting free blocks the same in both of these. But that's all right. And then we already did the test block, so we don't need to do that. We just check if free equals num, then we'll return that bit value where we started with all the free blocks. Okay. I don't know if that's slightly simpler than it was, but this kind of makes it work. And this test block is not really being used. I might leave it in, I might remove this later, but yeah, that should fix like one, maybe a little bit of issue using and allocating physical blocks. I don't think this will fix our current issue. Except it does, never mind. So if we can check beyond our current 32 bits and check into the next one, we can actually get accurate blocks that are free and eliminate a page fault issue. So that's good. So now when I load the file table, it shouldn't be at 18,000, it'll be at 15. See, before it was at 18 because it wasn't getting an accurate block reading. And I had facts and figures to back that up that I didn't save, so I'm sorry about that. I meant to take a screenshot, but I never did. But basically, if you looked at the start of memory for each bit that was set, the binary value, it was free around what corresponded to 15,000 in hex. But it was also free at 18,000. But we weren't getting 15 through 18 because test block didn't work. So that's why I went into and I changed the logic to be this, so we could check between blocks if it's free at the end of a current you know, 32-bit block. And that doesn't make sense, and I'm confusing myself. But anyway, the stuff works. We're fixing bugs, okay? Just trust me there. We're fixing bugs. We can still load programs. We can still run them. I know I keep doing this, but it's just a basic check I can do to make sure we can save and load a file. That's why I keep doing that. Checks to make sure stuff didn't change. The reboot works. Okay. So that's good. Fixed an issue there. Mark that off the list. Actually, I'll probably make the other things constant as well if I can. Are we messing with start address? We're getting a value to it. Size we're not. Let's see. Does this work if I do constant? I want to make all the things constant that should be constant. Or well, that don't change. Anything that we can make immutable, I'd rather make immutable so it works, right? And that works. Okay, base address and size. I'm not going full on operating system and Haskell level of pure functions, but you know, this way I can guarantee that these things won't be changed by these functions. So if I need them to change later, I'll have peace of mind that they won't be within these, which I think is good over time. Number blocks we're doing. The address, that's not changing either, is it? I'm setting it to starting block. Okay. So are we good? Do we const all the params within the physical memory manager? Are we good now? Can I satisfy my not OCD that we did that? I think we're good. Can we get a block and load it? We can. Okay, cool. Oh, there was the hardware issue with the date time. I mean, you're not going to see because it works in the emulator fine. But I reread the osdev wiki pages for real-time clock and CMOS. And it said that there should be a delay between reading a CMOS address, choosing it by doing like get RTC register, where I do this, where I write out what register I want to read to port 70. There should be a delay in between doing that and actually returning the data at that register. I didn't really have an issue on hardware, and I don't know how long the delay should be, but osdev wiki said there should be some sort of delay here. So I have an IOWait function in my ports file, which is just ports, which it waits one abstract IO cycle, which just reads in port 80, which shouldn't be used for anything. So I don't know how long that takes. I don't know if that's like 100 millisecond delay or 100 nanosecond or something. I don't know, but it's an imperceptibly small delay that I can put in. And I can also like stack it for more delay, right? So I'm just putting in one. A little wait between doing stuff whenever we read an address. So update in progress. I guess I can put something there, right? Small delay. And enable RTC. Small delay. Enable RTC, disable RTC, update in progress, disable RTC, so here. I think those are the only spots that I put that in. Yeah, that won't change anything. I mean, QEMU was iffy with date time regardless, right? Although it works with driftfix slew when I'm emulating. It's not 12:24 in the morning. This is UTC, and I am 5 or 6 hours behind that, but it works still, so we're good. Okay, I guess while I'm doing smaller changes, and that's still a couple changes in the makefile. The only changes were... I'll just remove that. Remove it if it's not needed. Adding that -i flag, and then if I'm adding... Oh yeah, because I'm going to have a small program later to test out malloc and free, and I didn't want to keep adding hard-coded stuff here. So this might ruin it a little bit if you try to build on Windows or something, I guess. You'd have to use like files first for %% in directory star.c, right? As an equivalent to what I'm going to do, but that's okay. Directory is a pretty good command on Windows, but what I'm going to do is set these, and I'm hoping this is POSIX compliant, but I'm just going to set these to all the assembly files in the source folder, or all the C files in the source folder. Right? Let me do that here. Move those down so I can have access to these as variable names. I'm going to use find for this. So I'm going to find within source directory. Can I do this? Is it this? Yeah, it's this, isn't it? Find all files with the name of whatever.c for each one of those file names. I'm going to execute another thing. I'm going to do base name. And base name will return the file name with the .c extension. I want to remove the extension, so I'm going to say remove the suffix -s of .c. So I'm hoping base name and find and all this is POSIX compliant, so as well as setting it equal in make. If not, then I'm losing portability. Oh well. But I'm going to do that for each object here that's returned with base name, and I have to escape the semicolon to end this explicitly. I'm going to do the same thing for assembly files. That and that. Except these will be .asm, and I don't want to include the boot sector. So I can add another condition here. Do not name bootsect.asm. So everything that isn't named bootsect.asm, but is an assembly file, just get the name of it without the extension of ASM. All right, and if I want to check that, I can do make, I think it's -V, C files, calculator, editor, and kernel. It'll be, yeah, it might be in alphabetical order now, depending how find finds the files. But it will still be the file names. Yeah, the ones that I actually want. So make -V, at least the one that I'm using, BSD make. This just gets the value, it evaluates the value of a make variable, which is what these are. So that way I don't have to hard code file names anymore for C or assembly. And I have them within these make variables that I use here, so we're all good. The only names that are hard coded are going to be bootsect and file table here for, I think, good obvious reasons. And I think that's it. So we can try making it again. It'll be in different order now, but that's all right. But it should still work. And it still works because we're loading these dynamically, sort of, from the file table within the boot sector. So yeah, everything's still good. These are in a different order, of course. So these will be in a different order, but the file sizes and everything are going to be the same. Files are still going to be able to be loaded the same. You know, we can still do all the other stuff the same. That was working. That was an invalid file name, so that didn't work, but you know, it all works. So that's all. That's the only thing I want to do within the make file. Okay, so I'm going to make, I think, the other changes for the kernel. I'm going to have to look up because I forget how I did it. So I'm going to change how we load files and programs within the kernel. Instead of hard coding things, allocated address block size. I mean, we get a sort of dynamic physical address. I guess we aren't hard coding, never mind. Instead of using a physical address though, I want to allocate a page and load to a page's virtual address. Okay, so in the kernel here, I want to change where we're loading files and programs and everything. This is for font, but I had another small like two other small changes, right? Very small, but it was to do with load file and I think delete file. And that was because right now, when you're reading this, it's like if load file was not equal to 0, and I mean that kind of in the C way, if it returns true or valid or something, then it was an error. I'd rather this return, you know, not 0 if it worked or 0 if it's an error. So I could do like if not load file, print the error string, right? Wouldn't that make more sense? So I'm going to change load file to do that, because I think that would make a lot more sense, right? If it didn't work, then say it didn't work. If it did, don't act like that's the wrong thing to do. You know what I mean? That doesn't need to be all the way out there. So if the file was not found, return 0. That way we can do if not load file, then it didn't work. If it was found, I'm going to return 1 for success. So that's the load file change that I wanted to do. The other thing was with delete file. Because if I delete something currently, it wipes out the start right here. It wipes out the directory entry. Let me put this full screen. Wipes out the directory entry, starting sector, and file size. So if I remove something in the middle of the file table and then I write something, it's going to write it. I guess it'll overwrite in the right place, but it'll look kind of weird. So I'm just going to get rid of this so that the space on the disk that is free will have the same space that it took up, right? I just think that makes a little bit more sense if we do it like that. Then I can change how load file works. I won't be able to load a file in the kernel though, so let me go back and do that. Load file, if it didn't work, I want to do not load file. Because then there would have been an error, and those are the only two places I call load file. Okay. And we'll just test this right quick. So if we delete something, let me make a file first. Let's make something. We should check if load works as well. Load file occurred. Oh, that's good. I guess loading doesn't work. That's always nice. I expected it to work, but I guess it didn't work. Well, we can load the editor, so that's good. Let me just make a file here. Test file 1. So if I delete test file 1, before it would have these be 0. Now it keeps the sizes. So that way if I make another file and it can be like up to this whatever size that the file was, it should be able to save and load. It'll just be easier to check, I think, within code, within a logic flow. And I think looking at it, it makes more sense. This is free. The amount of space that is free is this much space at this sector. So, you know, I don't know why file table failed to load. Oh, because that's in the editor and the editor doesn't have a changed load file. Yeah, let me change that. Forgot about that. And which is not the editor load file, but this one, if it equals to 0, just if load file worked, then it would be success. Because that makes more sense. And okay, that should have been the only thing there. So we'll see if loading a file works. Keep having to move this up. That's all right. We load the file table. Hey, there we go. It works. All right. I might have another bug here though. I'm just creating a binary file. Oh no, that works. I thought I had an issue before where it didn't actually go to the binary editor. That's okay. Okay, let's continue editing the kernel where I'm loading stuff. Like down here where I'm getting the needed blocks and everything. So instead of the number of blocks to load a file, I'm going to get the number of pages to load a file, and I'll call this num pages. File size times the number of bytes sector divided by size of a page in bytes. For file size in bytes to pages, and this will be pages. Okay. So I'm going to call this needed pages instead, and this will be divided by the page size. In effect, these are the same, you know, it's the same code because page size is block size at this point. I'm just calling this something different semantically to make more sense. But instead of doing if 0 equals 1, I'm just going to do if the size modulo page size is not 0, then I'll add a page. I'll just do that. Or greater than 0, I guess. Yeah, 5 corner modulo page size. Oh, this greater than 0. Then we'll add needed pages plus plus, which I wasn't doing that before. So there could have been situations up until now where we weren't actually loading the complete file or program by like 4K up to 4K because I wasn't doing this. So that probably fixed a future bug, hopefully. Allocate extra page for partial page of memory, I guess, whatever. So instead of allocating blocks, we'll allocate pages, and I'll call it pages. We're not allocating to this address. We're going to allocate to a virtual address instead. I know I got rid of that line. I'll replace it with a thing here. And I'm going to make a sort of a little constant here. I'm going to make what I'm going to call an entry point. So if you think of something like an ELF file format as an entry point, a PE file for Windows has an entry point that a program is loaded to. So in this case, a file or a program is going to be loaded to a set entry point, and through the magic of paging and virtual memory, we can have the same entry point for multiple processes. So I think in ELF file 64-bit, at least under the GNU linker, it set it to, on FreeBSD, so you know all these stipulations, it was set to 4 meg or 400,000. A couple months before recording this video, maybe 1 or 2 months, I was working on an assembler, which isn't finished, but I got pretty far along. And I got into writing a basic ELF and PE file, just the bytes to a file that the bytes corresponded to the ELF file section. So it was a valid file that I wrote, hand wrote the bytes, and then abstracted out a bit, added to my assembler. And depending on the linker I was using, it was setting the entry point differently for the ELF headers and stuff. And I was like, why is it at 400,000? So it makes sense now, after identity mapping the first 4 megs, that maybe they set 400,000 to be right after the first 4 meg page table. I think that would make sense from an OS standpoint. So I'm going to set my entry point similar to that, 400,000 in hex, which is 4 meg. I'm going to put load files programs to this starting address. And we can use the same one for multiple processes, which is awesome because they would end up being mapped to different physical addresses when I develop processes and things. At any rate, I'm setting the entry point to 4 meg to correspond to right after the first identity mapped 0 to 4 meg, addresses. All right, put entry point right after identity mapped 4 meg page table. All right, so however many pages we need that we got from the file size, I want to allocate those pages. I'm going to allocate and map those in, mark them as present, and read write so we can actually load stuff to there and not get page faults, right? So let's do that. Get the needed pages in a loop here. So we'll make a new page out of the other. We'll conjure it up. I'm going to say, hey, this page needs an actual physical address. And that is going to be wherever we allocate a page to. So we had allocate page. We had this function here to allocate a block for a page and set that as the frame for the physical address for the page. That's what we're doing here. We're saying, hey, give us a new block of memory, put it as the physical address, or well, return that physical address rather for this page. I'm sorry I moved the cursor around. I'm sorry I'm doing this when I'm talking. That's probably annoying to some people. I'll try to not do that. I'll try to not do that. Okay, so if we try to map this page and it doesn't work, I'm going to have an error, but assuming it does work, I'm going to try to map the address for this physical address that was returned, this new block of memory. I want to map that to a virtual address starting at this entry point. Okay, and then however many pages we need to allocate, I'm going to offset from that entry point, and it will get a new page, a new physical block of memory every time. So the virtual addresses can increase at a constant rate to make sense for whatever program wants to use things. But the physical addresses these pages are mapped to can be all over the place. It'll be wherever we have free memory that is being allocated. But the virtual addresses can be a sort of constant rate here. So we'll say I times the page size. So the first page will be mapped to 400,000. The next page will be mapped to 401,000, because 1,000 in hex is 4,096 bytes. The next one will be 402,000, so on and so forth. So it'll make more sense from an OS developer standpoint, to do it this way. It's easier to do it this way. Then we can have programs use whatever addresses they want, and we can link them better later and offset them from this address, and it'll line up and be cool. But I'm not in the business of making a linker just yet. A bit out of my wheelhouse. But assuming the page was mapped all right, we'll go on. If not, we want an error. Maybe the page didn't work. I'm going to print that we're out of memory and can't map the page. So kernel cursor X, kernel cursor Y. Couldn't map pages. Maybe out of memory. And give a sad face. I do have a sad face in my diff, so I'm just adding that because I already did that before. But unlike Windows oops, something went wrong, I at least tell you we couldn't map pages. So I could probably say couldn't map to this address, but right now I'll just leave it right there. And I'm gonna, I guess I don't need to halt, we can go back. But assuming it worked, we will have mapped the page, and this will be all right. So we'll map all the pages to virtual addresses starting at 400,000. Physical addresses can be wherever is located from the memory manager, so we kind of abstracted that out. That's not hard-coded, that's good. We're going to print we allocated that to a virtual address. It'll just allocate to the entry point right now, because that's where it's going to start every time. So this will be kind of static, that's okay. And it is a 32-bit, so we can do that. These, I guess I could make, you know, R in, because those are returned as 10 and 13. So that's a little bit shorter. I should probably do that for all these strings. It's a little bit shorter. So here, load file, we're going to load it to the entry point, which will be the same address every time, so that's good. Load to, put starting memory address. Entry point is a 32-bit, so we don't need to cast it. Okay. So the other changes are here. I'm going to have variables later, so I guess I'll put a to-do here. This is kind of reaching from the future, but I'm going to make a malloc implementation. And if my program that I'm loading here wants to allocate memory dynamically, I'll have a couple global variables inside of our malloc, but I'm going to reset those variables here, and then I'm going to reset them after the program returns. And this is just to fix some errors at runtime that happened in emulation and on my hardware. Faulty dangling pointers that weren't freed correctly or using things after free and other issues. So this is for later. I'm just putting to-dos here. Sorry, it won't make sense right now, but before and after. All right. But the allocated address is going to be the entry points. I'm not sure what else I need to change at the moment. Oh, free in pages when done. Free memory when done. This will be free pages when done. And I'll also have a thing. I'm going to have another to do here in case we malloc stuff later. If used malloc, free remaining memory to prevent memory leaks. We'll do that here. Okay, but right now we're just freeing pages. Instead of needed blocks, this will be needed pages. And the address will be the entry points. You know what I could do is do this, right? So, that's not gonna work, is it? I would have to do a double. Double? I want to replace these. Replace that with our in. Bam! Look at there. That's how you use sed and vim. Okay. Of course, I'm at the bottom of the file now. There we go. Thank you, Control-O jump list. So we're freeing these pages, not blocks. Pages, read address, entry point, which is a uint32. Previously allocated pages when done. Should be here. This will be similar to the allocate loop that we did to allocate pages. Except I'm going to unmap the pages instead of mapping the pages, and I'm going to free them. So we're going to start at the entry point and go until, you know, however many pages we mapped. Since we conveniently... Where is it? I lost my place. Oh, since we conveniently added each page at a virtual address offset by the page size from the entry point, we can use those same addresses as input to unmap those pages. So it kind of lines up nicely. I less than needed pages, I++, and we'll increase the vert address by the page size. But similar to what we had above, we'll have a page. I'm going to make a pointer actually. Page will be getting a page for that virtual address, that page that was allocated earlier. If that page has a physical address, if it was not freed or unallocated by this point, it'll have a valid physical address associated, you know, in the page frame of the page itself. So if there is a physical address, it'll be above 0. This will return true. So, and here I'm using test attribute. If there is a physical address and it is present, so we don't have to unallocate an unpresent page because it's already been unallocated before, or it's just, you know, not being used. But if it has an address associated and it's present, so it's being used in memory right now, then I want to free it and unmap it. So I'm going to call free page. I guess that just takes a pointer. Okay, free page. Here. And that will call free blocks. So that'll free the physical memory and the physical memory manager for that address that the page has. And it'll clear the present bit, so it won't be present anymore. After we free that, I also want to unmap it. I think that takes... Why do I keep doing this? This is a pointer, not a physical thing. That takes a void address. Yeah, void pointer. So I need to cast that. I don't need to cast it, but I'll cast it to uint32 for vert. I guess I could cast it to a void pointer, but I guess our sizes right now are 32-bit addresses, so whatever. You could do this a few different ways. But I want to unmap the page at that address, set the physical address to 0, and then also clear the present flag, which is already cleared, but whatever. A little redundant, but that's fine. But after we unmap a page and it's not present, we're not going to use it, it doesn't point to a valid address, I'm going to invalidate the page in the translation look-aside buffer so that we don't try to access it again unless it's mapped again later. So flush TLB entry for that address. So this will be invalidate page as it is no longer present or mapped. Okay. So that'll just fix some other issues. Trying to access non-valid pages, we won't look at them because they won't be in the cache. If we access this address in the future, then it will reload the new page for this address into the TLB. Otherwise, it would use a sort of stale page that may or may not be true since it's been unmapped. We want to make sure it's not stale. We want to get a fresh one if we use this address again. So we want to invalidate it after we unmapped. All right. This will be entry points. The allocated address may not be a variable anymore. After this, we want to do similar things to free the pages after we print the file out. Yeah, free memory. I'll do free pages. Free pages when done. Print character. This could just be print string. I'm noticing now this could be print rn, because that's all I'm doing. Save a line. How to save a line. Okay. Freeing needed pages. Read at address, entry points. And this is going to be like what we did up here. It might be the same code actually. So that's kind of duplicated. I could abstract that to a little helper function or something. It says, you know, free allocated pages at entry point. Very verbose. Free data address entry. Okay, whatever. We'll go with this. We'll just use the same code because we can extract it out later to deduplicate things. The other change was here. I don't need a to-do because I'm printing this out. Just saw that in my diff page. Okay, we'll see if this works. For loading stuff using pages, which it doesn't, because that's implicit. Which is great. What is it called? Page fizz address. What did I call it? Oh, adder. Address. Spell out the full word. That would help, wouldn't it? It would help if I didn't capitalize that M, or made it an alias, so I stopped typing that. Okay, can I load something? And because I failed at making, now the file table is huge and I have to do it again. Okay. I should make that, not do that, but whatever. So I can load a thing, a page, allocated here. So we allocated a block of memory. We mapped it to this entry point address. We loaded to that address. We read a file to the screen, and we freed a page at that address. I mean, we could check if we have a memory leak by seeing if this value is the same for the available blocks before and after we call stuff. So 28535. 28535. If we had a memory leak of one or more pages, then this number would be lower, right? It wouldn't be the same before and after a program or file would be called. 3. I don't have decimal, yeah. That's good. So the editor is a few. Test I, yeah, I'll spell that wrong. That's fine. That's the same. So test IL1. The same. Can I rename? Oh, I can rename stuff. That's good. Okay. So we're loading to pages. That's good. So what else do I have to do in this video? Well, the last major part is writing malloc and free. So I'm going to write 2 small syscalls and sort of C functions that'll be wrappers to these system calls for malloc and free. Malloc will take in a byte number, like if I call, I don't know. I want a character pointer, say, or a pointer to memory, to malloc 100 bytes. So I want to be able to do something like this within like the editor, another file, another program that's loaded, and get dynamic memory. So I'm going to make something, an interface to actually call malloc that'll be used like this, and then later on we'll free the memory at the pointer, right? So I'll make malloc and free system calls, C functions, that will effectively be wrappers to those system calls. And I will make a malloc implementation file, probably just using a linked list, really basic example, with linked list nodes that point to whatever memory is being returned, and that memory will have a size of whatever you want it to malloc. So we'll have a node of 100 bytes, if we called malloc 100. We'll return a pointer to 100 bytes. And then we'll free out a pointer, and I'll search through my linked list nodes, and if we reach a memory address that has previously been malloced, and that address matches the pointer that we're freeing, then I'll mark that space for that node as free. And that's kind of how malloc and free will work within this. So I'm going to do that next, and that I think will be the last thing I'm doing in this 5-hour-long session that I'm recording. So that'll be good. And then I'll fill in a couple of these to-dos, right? In case we malloc, I need to prevent memory leaks. But yeah, I'll get to that.